Constant. 9 hours before dawn, the barometer at Saipan International Airport fell through 950 millibars, and the anemometer needle stopped bothering with the low end of the dial. Constant sustained winds above 120 miles per hour, not gust spikes, sustained. Constant for over 9 consecutive hours already, and the eye wall, the innermost violent ring of the strongest tropical cyclone spinning anywhere on planet Earth right now, has not yet arrived. Constant, that storm is Super Typhoon Silica. Constant, a Category 5 with peak sustained winds of 173 miles per hour. Constant. It is currently making landfall on American soil, on islands that never fully recovered from the last catastrophe, and 6 hours before its eye wall crossed the coast, a magnitude 5.5 earthquake shook the same island chain from underneath. Constant. And while all of that is unfolding in the Western Pacific, the rest of the United States is cracking apart in parallel. Constant record heat on the East Coast, tornadoes spinning up across the Midwest. Constant wildfires burning through the plains, flooding through the Great Lakes. Constant every category of atmospheric hazard firing on the same day, on the same country, on the same overloaded response network. Constant. This is the Cosmic Forecast, and if this hook has landed the way I think it just landed, subscribe to the Cosmic Forecast so you don't miss what comes next, because this story is just getting started. Constant. Drop a comment below. Constant. I want to know where in the world you are watching from, what time it is where you are, and your honest take on the question at the centre of this entire video. Constant. If this is what the climate system produces in April, in a neutral ENSO year, before El Niño has even entered the picture, what exactly does peak season look like now? Constant. Tell me what you think. Now settle in because we have a lot to unpack. Constant. Right now, as you are watching this, the strongest storm on the planet is tearing across American soil, and almost nobody on the mainland is talking about it. Constant. Saipan International Airport has been recording sustained winds above 120 miles per hour for over 9 consecutive hours. Constant. 9 hours. That is not a gust, that is not a peak reading that spiked and dropped. Constant. That is 9 straight hours of wind strong enough to shred commercial roofing, snap power poles like matchsticks, and turn everyday objects, garbage cans, road signs, sheets of corrugated metal, into projectiles moving faster than a Major League fastball. Constant. And here is the part that should stop you cold. Constant. Those 9 hours of carnage that was before the eye wall arrived. Constant. Let me say that again so it registers. Constant. Everything I just described, the airport readings, the structural damage already underway, the flash flooding already pooling across low-lying roads, all of that is the warm-up act. Constant. The eye wall, the narrow ring of a tropical cyclone where wind speeds hit their absolute maximum, is only now crossing the islands. Constant. What residents on Tinian and Saipan have been enduring for the better part of a day is the equivalent of getting hit in the gut over and over for hours, and then being told that the actual fight has not started yet. Constant. The National Weather Service has issued an extreme wind warning for these islands. Constant. If you have never heard of that alert product, there is a reason. It almost never gets used. Constant. This is the rarest, most severe wind warning in the entire American forecasting system, reserved exclusively for the inner core of the most violent tropical cyclones, where sustained winds are expected to reach or exceed 150 miles per hour. Constant. It is the kind of warning that essentially tells you that if you are not already inside a reinforced concrete structure, there is nothing left to do. Constant. The atmosphere outside is no longer survivable in any conventional sense. Constant. And that warning is active right now over United States territory. Constant. Radar imagery from Andersen Air Force Base on Guam is confirming what forecasters feared. Constant. The eye wall is not making a clean pass to one side of the islands. Constant. It is directly crossing Tinian, and the outer edge of that same eye wall is clipping Saipan. Constant. 2 populated islands, both inside the most destructive part of the storm simultaneously. Constant. There is a concept in structural engineering called fatigue loading. Constant. It is the idea that buildings and infrastructure do not necessarily fail because of a single extreme force. Constant. They fail because of repeated stress cycles. Constant. You push a beam one way, then the other, then back again thousands of times. And eventually the material gives out, not because any single push exceeded the design limit, but because the cumulative load wore through its resistance. Constant. That is what 9+ hours of hurricane force winds does to a building. Constant. Every gust flexes the roof, every sustained blast pushes the walls, fasteners loosen. Constant. Joints separate, microfractures propagate through concrete. Constant. By the time the eye wall arrives with winds 50% stronger than what has already been hitting, the structures are not at full strength anymore. Constant. They have been pre-weakened, and that is when the real force shows up. Constant. Rain has been falling at rates between 1 and 2 inches per hour across the island chain. Constant. On flat continental landmasses, that kind of rainfall is manageable. Storm drains handle it. Constant. Rivers swell but hold, but Tinian and Saipan are not flat continental landmasses. Constant. These are small volcanic islands with steep interior terrain, thin soil layers over rock, and drainage systems that were marginal even before the last few typhoons chewed through them. Constant. Water does not soak in, it runs off fast down slopes, across roads, through structures, carrying debris and mud with it. Constant flash flooding is already underway, and the heaviest rain bands have not even locked in yet. Constant, and then there is the ocean itself. Constant storm surge forecasts are calling for 10 to 15 feet of water above normal tide levels. Constant waves offshore are running at 40 feet. Constant. The reef systems that normally buffer some of that wave energy are already being overtopped, which means the full force of the open ocean is reaching the coastline with almost nothing to slow it down. Constant coastal structures, docks, seawalls, beachfront buildings, they are taking direct wave impacts on top of the surge, on top of the rain, on top of the wind. Constant. Every hazard is stacking on top of the last one, and none of them are letting up. Constant. This is the key thing that separates this event from most storms you have seen covered on the news. Constant. This is not a hit-and-run typhoon. Constant. It is not racing across the islands at 20 or 30 miles per hour, delivering a brutal but brief punishment and moving on. Constant. This storm is barely moving. It is sitting on top of these islands like a weight pressing down. Constant. And every hour it stays, the damage compounds in ways that are not linear. Constant. We will get into exactly why that slow motion is so dangerous in a moment. Constant. But first you need to understand what kind of storm we are actually dealing with. Constant. Because this is not just a strong typhoon that wandered over some islands. Constant. This is the most powerful cyclone currently spinning anywhere on the planet. Constant. And it has no business existing in April. What happens when a Category 5 does not move? Part 2. Constant. The strongest storm on Earth right now. Constant. Super Typhoon Sinlaku reached peak sustained winds of 173 miles per hour. Constant. Let that number breathe for a second. 173. Constant. That is 278 kilometers per hour for anyone watching outside the United States. Constant. That is faster than the cruising speed of some propeller aircraft. Constant. That is a storm generating winds that exceed the design specifications for most residential and commercial structures ever built on these islands. Constant. At the moment of peak intensity, there was no tropical cyclone anywhere else on the planet. Constant. Not in the Atlantic, not in the Indian Ocean, not in the southern hemisphere, that came close. Constant. Sinlaku was the strongest storm on Earth, full stop. Constant. Now if you follow this channel, you know I do not throw around superlatives just for drama. Constant. So let me put this in a framework that actually means something. Constant. In the Western Pacific, the Joint Typhoon Warning Center classifies any typhoon with sustained winds of 150 miles per hour or greater as a super typhoon. Constant. That threshold is roughly equivalent to a strong Category 4 or a Category 5 on the Saffir-Simpson scale used in the Atlantic. Constant. Sinlaku did not just clear that bar, it vaulted over it. Constant. At 173, it is comfortably in the upper tier of super typhoons, the kind of intensity that historically shows up maybe a handful of times per decade. Constant. And it showed up in April. That is the detail that should reframe everything you are hearing. Constant. April is not typhoon season. Constant. The Western Pacific's primary cyclone season runs from roughly July through November, with peak activity concentrated in August, September and October. Constant. That is when ocean heat content has had all summer to build up, when atmospheric moisture is maximised, when the monsoon trough sets up favourable rotation patterns. Constant. April is the tail end of the dry season in the Marianas. Constant. It is a month where you might see a weak tropical depression wobble across the basin and dissipate. Constant. You do not see 173 mile per hour super typhoons, but here we are. Constant. And the reason I keep circling back to the timing is that the timing is the story. Constant. A Category 5 in September is terrifying but expected. A Category 5 in April is a signal. Constant. It is the climate system telling you that the old calendar, the one where cyclone season had a start date and an end date and you could plan around it, that calendar is becoming unreliable. Constant. To find a historical comparison, you have to reach back to Typhoon Hester in 1966. Constant. Hester formed in late March and strengthened into a super typhoon in early April, making it one of the only documented cases of a storm reaching this intensity so early in the year. Constant. But that was 60 years ago and it was treated as a freak event, a statistical outlier in a dataset too short to draw conclusions from. Constant. Sinlaku in 2026 makes the pattern harder to dismiss. Constant. When outliers start repeating, they stop being outliers. Constant. The energy involved in a storm like this is almost incomprehensible. Constant. Kerry Emanuel at MIT, whose 1987 paper in Nature titled The Dependence of Hurricane Intensity on Climate, essentially founded modern tropical cyclone thermodynamics, has spent his career reminding people that a mature super typhoon releases thermal energy at rates that dwarf anything humans have ever engineered. Constant. We are talking about continuous heat output equivalent to several times the total electricity consumption of a major industrialized nation, sustained for days. Constant. The storm is essentially a massive heat engine pulling thermal energy out of the ocean surface, converting it into kinetic energy, wind, and radiating waste heat out the top of the storm into the upper atmosphere. Constant. The efficiency of that engine depends on the fuel supply, and the fuel supply is ocean heat. Constant. Under normal April conditions, the ocean in the western Pacific has not yet accumulated enough heat to sustain that kind of engine at full output. Constant. The upper ocean layers are warm, sure, but the heat does not extend very far down. Constant. And storms that try to intensify churn up cooler water from below, effectively cutting off their own fuel supply. Constant. It is a natural braking mechanism. The ocean gives, then it takes away. Constant. But this year that mechanism failed. Constant. And the reason it failed is one of the most important parts of this entire story, because it connects this single storm to something much larger. Constant. A pattern that keeps showing up in the data event after event, year after year. Constant. There is another number worth sitting with before we go deeper. Constant. The minimum central pressure of Sinlaku bottomed out at approximately 908 millibars. Constant. To translate that, standard sea level pressure is 1013.25 millibars. Constant. Every millibar you drop below that represents a huge amount of atmospheric mass that has been evacuated from the storm's core. Constant. At 908, you are looking at a pressure deficit of over 100 millibars, which is a threshold that only the most intense tropical cyclones in the historical record have ever reached. Constant. For context, Hurricane Camille in 1969 bottomed out at 900 millibars. Constant. Typhoon Tip in 1979 reached 870, the lowest reliably measured sea level pressure in tropical cyclone history. Constant. Sinlaku is not the strongest storm ever measured, but it is comfortably in the elite tier, and it is the strongest of 2026 by a significant margin, and again this is April. Constant. If April can produce a 173 mile/hour super typhoon with a central pressure below 910 millibars, what exactly does peak season look like now? Constant. That question is going to come back at us from a dozen different angles as we work through this. Constant. Hold it in your mind, part 3, the slow motion catastrophe. Constant. There is a number buried in the forecast data for Super Typhoon Sinlaku that matters more than wind speed, more than pressure, possibly more than any other single variable in this entire event. Constant. And most people scrolling past the headlines will never even see it. Forward speed 3 knots. Constant. That is roughly 3.5 miles per hour, about 5.5 kilometers per hour. Constant. To put that in terms you can feel, that is slower than a casual walk. Constant. You right now watching this from your couch could get up and outpace this Category 5 Super Typhoon on foot. Constant. And that is what makes this storm a potential worst case scenario. Constant. When we talk about tropical cyclone damage, the public conversation almost always fixates on wind speed. Constant. Category 1, Category 3, Category 5. Constant. Those labels are based entirely on maximum sustained winds, and yes, wind speed matters. Constant. Higher winds mean more force on structures, more airborne debris, more immediate destruction. Constant. But wind speed is only half the equation. Constant. The other half, the half that emergency managers lose sleep over, is duration. Constant. How long does a community sit inside the damage zone? Constant. How many hours are the winds tearing at the same buildings, the rain falling on the same watersheds? Constant. The surge pushing water into the same streets? Constant. A Category 5 typhoon moving at 20 knots, which is a fairly typical forward speed, might subject a given island to peak conditions for 2, maybe 3 hours. Constant. That is catastrophic, but it is bounded. The storm arrives, delivers its worst, and exits. Constant. Emergency response can begin within hours of the eye wall's passage. Constant. With Sinlaku crawling at 3 knots, that same island could experience eye wall conditions for 8 to 10 hours, maybe longer. Constant. The math on rainfall alone tells you what that means. Constant. At a rate of 1 to 2 inches per hour, which is what is already being observed, a 3-hour passage dumps 3 to 6 inches. Constant. Manageable for many locations, dangerous for small islands, but within the range of historical precedent. Constant. A 10-hour passage at the same rate delivers 10 to 20 inches. Constant. And that is the conservative estimate. Constant. The National Weather Service forecast for this event is 15 to 25 inches of total rainfall across the Mariana Islands. Constant. Some localized areas could see more. This is where the non-linear nature of disaster kicks in. Constant. Doubling the rainfall does not double the flood risk. Constant. It can increase it by a factor of 5 or 10, because drainage systems that can handle a certain flow rate become overwhelmed. Constant. And once they are overwhelmed, every additional inch of rain has nowhere to go except across the surface, through buildings, down slopes, and into communities. Constant. On volcanic islands like Tinian and Saipan, the terrain amplifies this dramatically. Constant. Steep hillsides shed water almost instantly. Constant. Thin topsoil over volcanic rock means virtually zero absorption. Constant. The water becomes a gravity-driven weapon, picking up speed, picking up debris, carving channels where roads used to be. Constant. And this brings us right back to the central problem. This storm is not just strong, it is slow. Constant. And slow in the context of tropical cyclones is a multiplier that transforms every other hazard from dangerous to potentially unsurvivable. Constant. If you want a mainland comparison, think about Hurricane Harvey in 2017. Constant. Harvey stalled over the Houston metropolitan area for days, dumping more than 60 inches of rain in some locations. Constant. It was not Harvey's wind that made it a historic disaster. It was the fact that it stopped moving. Constant. The storm sat over one of America's largest cities and simply kept raining. Constant. The floods that resulted were unlike anything modern Texas had experienced. Constant. More than $100 billion in damage. Constant. Over 100 people killed, the majority from drowning in floodwaters, not from wind. Constant. Sinlaku is not Harvey. The geography is completely different, the population base is far smaller. Constant. And the storm dynamics are not identical, but the principle is the same. Constant. When a tropical cyclone stops moving, duration replaces intensity as the primary driver of destruction. Constant. The storm surge compounds this. Under normal conditions, storm surge is a temporary phenomenon. Constant. The cyclone pushes a dome of water ahead of it. Constant. The water rushes inland as the storm arrives and then it recedes as the storm passes. Constant. With a slow-moving storm, the surge does not recede, it sits for hours. Constant. Water that would normally drain back to sea stays pushed against the coastline, flooding everything near shore for far longer than structures and terrain are designed to withstand. Constant. To 15 feet of surge for 1 hour is devastating. Constant. 10 to 15 feet for 8 hours is transformative. It reshapes the coastline itself. Constant. And every hour this storm lingers, it is grinding down the same infrastructure, the same buildings, the same power systems, the same communications networks that were already compromised before the storm even reached peak intensity. Constant. Remember, these islands had 9 hours of hurricane-force winds before the eye wall arrived. Constant. The structures being hit by the eye wall right now are not at full design strength. Constant. They are already damaged. Constant. They are taking the worst punch of the fight with their guard already broken. Constant. This is just about strength, it is about time under pressure. Constant. And the islands absorbing this pressure have a history that makes everything worse, because they were never whole to begin with. Constant. There is a paper worth mentioning here. Constant. James Cossin, then at the National Oceanic and Atmospheric Administration, published a study in Nature in 2018 titled A Global Slowdown of Tropical Cyclone Translation Speed. Constant. The finding was that between 9,949 and 2016, the average forward motion of tropical cyclones globally slowed by about 10%. Constant. In the western North Pacific, the region we are looking at right now, the slowdown over land was even more pronounced. Constant. 10% is not a small number. Constant. It means that every storm on average spends 10% longer over any given point on its path. Constant. 10% more rain, 10% more surge duration, 10% more fatigue loading. Constant. Cossin's paper does not claim every storm will slow, and there has been legitimate scientific back and forth on the methodology since it was published. Constant. But the direction of the signal is now supported by multiple follow-up studies. Constant. Slower storms are becoming more common. Constant. And when a slow storm happens to be a Category 5, you get exactly what is happening over Tinian and Saipan tonight. Constant. Part 4. The islands that did not recover. Constant. In October of 2018, Super Typhoon Yutu made a direct hit on Tinian and Saipan with sustained winds of 180 miles per hour. Constant. It was the strongest tropical cyclone to strike any part of the United States since records began. Constant. Not the strongest that year, not the strongest in the Pacific, the strongest to ever hit US. Constant. Soil period. Yutu essentially flattened Tinian. Constant. Post-storm surveys showed that the majority of structures on the island sustained significant to catastrophic damage. Constant. Concrete buildings had their roofs peeled off. Constant. Wooden structures were reduced to scattered debris fields. The power grid did not just go down. Constant. It was physically destroyed, transmission poles snapped. Constant. Distribution lines ripped from their anchors. Constant. The entire electrical network rendered non-functional in a matter of hours. Constant. Communications infrastructure collapsed alongside it. Constant. Cell towers were toppled or stripped of their equipment. Landline networks were severed. Constant. For days after Yutu, Tinian was effectively cut off from the outside world. Constant. An American community in the 20th century reduced to pre-industrial communication capabilities. Constant. The recovery from Yutu was long, expensive and incomplete. Federal disaster assistance flowed in. Constant. But the Commonwealth of the Northern Mariana Islands, the CNMI, is not a wealthy territory. Constant. The local economy is small, heavily dependent on tourism and federal support. And the fiscal infrastructure needed to manage large-scale reconstruction simply was not scaled for an event of that magnitude. Constant. Buildings were patched rather than rebuilt to modern code. Temporary fixes became permanent. Constant. Power restoration took months in some areas. Constant. And even after the grid was nominally functional again, it remained fragile, vulnerable to disruption from far less severe events. Constant. And then came Typhoon Mawar in 2023, which passed near enough to Guam and the southern Marianas to inflict additional damage on systems that were still recovering from Yutu. Constant. Another round of repairs, another draw on limited resources. Constant. Another set of buildings weakened and patched and weakened again. Constant, this is the cycle that defines life in the CNMI. Constant, and it is the cycle that makes Super Typhoon Sinlaku so much worse than its wind speed alone would suggest. Constant, the islands absorbing this storm are not starting from baseline, they are starting from a deficit. Constant, every structure standing today has a history written in its walls, patches over patches. Constant, repairs that were good enough to pass inspection but not good enough to withstand another direct hit at Category 5 intensity. Constant, the concrete that survived U2 has been through thousands of thermal expansion cycles, salt exposure, moisture infiltration, and the constant low-grade seismic activity of a volcanic island chain. Constant, it is not the same concrete that was poured when those buildings were new. Constant, there is a concept that disaster researchers have been talking about with increasing urgency, and I think it crystallizes exactly what we are watching unfold. Constant, they call it the recovery gap. Constant, the recovery gap is the space between how long it takes a community to rebuild and how often the next disaster arrives. Constant, when the recovery period is shorter than the return interval, communities can fully restore their infrastructure, their economy, and their social fabric before the next event. Constant, but when storms come faster than communities can rebuild, when the gap closes or inverts, you get a ratchet effect. Constant, each storm pushes the baseline lower, each recovery reaches a lower ceiling. Constant, and over time the community is not recovering at all. Constant, it is in a managed decline, absorbing repeated blows with diminishing capacity to absorb the next one. Constant, the CNMI is living inside that gap right now. U2 in 2018. Constant, Mawar in 2023, Sinlaku in 2026. Constant, 3 major cyclone events in 8 years. Constant, each one hitting infrastructure weakened by its predecessor. The math does not work. Constant, you cannot fully rebuild a power grid, housing stock, water system and transportation network on a remote Pacific island in 3 to 5 years on a limited budget, while maintaining normal government services and economic activity. Constant, it is not possible, so what happens instead is triage. Constant, the most critical systems get partial restoration, everything else degrades. Constant, and now a 173 mile/hour super typhoon is sitting on top of those partially restored systems, grinding them down for 8 to 10 hours. Constant, the question that should be forming in your mind is not whether these islands can survive this storm. Constant, people are resilient, communities endure. Constant, the question is why storms like this keep showing up faster and harder than the recovery cycle can handle. Constant, and to answer that we need to go beneath the surface, literally. Constant, there is one more piece to this that I do not want to skip past because it comes up in every disaster analysis of the CNMI and it never quite gets the attention it deserves. Constant, the population of the entire Commonwealth of the Northern Mariana Islands is roughly 47,000 people. Constant, Tinian by itself has around 2,000 residents. Constant, Saipan carries most of the population, around 43,000. Constant, these are not abstract statistics. Constant, these are 47,000 American citizens, most of them concentrated on a couple of small islands in the middle of the Pacific, whose nearest major disaster response staging area is Guam, whose next nearest is Hawaii, whose next nearest is the continental United States. Constant, when U2 hit, mutual aid did not roll in from the neighbouring county because there is no neighbouring county. Constant, there is no highway network, there is no adjacent state whose National Guard can convoy over. Constant, every asset that comes in has to come in by air or by sea, and both of those channels are affected by the same storm you are trying to respond to. Constant, this is not a criticism of federal response. Constant, FEMA has done what it can with the constraints of geography. Constant, it is a description of the geography itself. The CNMI does not have redundancy. Constant, and when Sinlaku is done tonight, the CNMI will once again be relying on that same air and sea corridor to bring in the personnel, the fuel, the water, the generators, and the building materials that make recovery possible. Constant, on top of a corridor that already has to serve normal supply needs. Constant, on top of a corridor whose costs are borne by a territorial economy that was already stretched thin before this storm formed. Constant, Part 5, the ocean beneath it, every tropical cyclone on Earth runs on the same fuel. Constant, warm ocean water, that is it. Constant, strip away the satellite imagery, the radar loops, the wind speed moments, and what you are looking at is a heat engine. Constant, the ocean provides thermal energy, the atmosphere converts it into motion. Constant, the storm is just the visible expression of that conversion, but not all fuel is created equal. Constant, and the ocean conditions underneath Super Typhoon Sinlaku are abnormal in a way that helps explain why this storm exists at all, and why it reached the intensity it did in a month when it should not have been able to. Constant, ocean heat content beneath the storm's track has been measured at approximately 125 to 150 kilojoules per square centimetre. Constant, that number may not mean much to you in isolation, so let me contextualize it. Constant, the generally accepted threshold for sustaining a tropical cyclone is around 50 to 60 kilojoules per square centimetre. Constant, the threshold for rapid intensification, the kind of explosive strengthening that turns a modest typhoon into a Category 5 overnight, is roughly 80 to 100. Constant. Sinlaku was riding over ocean heat content that was 50 to 75% above the rapid intensification threshold. Constant. In April. Constant. Sea surface temperatures along the storm's path were running between 28 and 29 degrees Celsius. Constant. The conventional threshold for tropical cyclone development is around 26 to 27. Constant. So surface temperatures were above threshold, which is not terribly unusual for the Western Pacific, even in spring. Constant. But the critical factor is not what is happening at the surface. It is what is happening underneath. Constant. Most of the time, a powerful typhoon is its own worst enemy when it comes to intensity. Constant. The strong winds at the ocean surface churn the water column, mixing cooler water from below up to the surface. Constant. This process, called upwelling, reduces sea surface temperatures directly beneath the storm, cutting off the thermal energy supply. Constant. It is a natural negative feedback loop. Constant. The stronger the storm gets, the more it disrupts its own fuel source. Constant. This is why many typhoons reach a peak intensity and then gradually weaken, even if atmospheric conditions remain favourable. Constant. The ocean pulls the plug. With Sinlaku, the ocean did not pull the plug, and the reason is depth. Constant. The warm water beneath this storm's track extends far deeper than normal. Constant. Instead of a thin warm layer sitting on top of a cooler thermocline, the heat goes down and down and down. Constant. When the storm's winds churn the surface, the water mixing up from below is still warm. Constant. The negative feedback loop that should limit intensity simply does not engage. Constant. The storm keeps drawing energy, keeps intensifying, keeps sustaining winds that should be physically impossible for the season. Constant. This is what oceanographers refer to as warm pool expansion in the Western Pacific. Constant. The warm pool, that massive region of water above 28 degrees Celsius that drives so much of the planet's weather, has been growing in volume and extent for decades. Constant. It is not just spreading geographically, it is deepening. Constant. More heat stored deeper in the water column, available for longer, resistant to the self-limiting mechanisms that used to keep early season storms in check. Constant. This is not a fringe observation. Constant. A 2020 paper by Cheng and colleagues in Advances in Atmospheric Sciences documented that ocean heat content in the upper 2,000 meters of the world's oceans reached a new record high in every recent year, with the Western Pacific among the fastest warming basins. Constant. A separate study by Trenberth and colleagues at the National Center for Atmospheric Research quantified the imbalance between incoming solar radiation and outgoing thermal radiation, and found that the difference, the net accumulation of heat in the Earth system, is overwhelmingly more than 90% going into the oceans. Constant. The atmosphere gets the headlines, the ocean gets the heat. Constant. And this connects directly to the central question of this entire event. Constant. A super typhoon in April should not have access to this kind of energy. Constant. The seasonal accumulation of solar heating should not have pushed ocean heat content this high this early. Constant. But the ocean is not resetting to zero each winter anymore. Constant. It is carrying over anomalous warmth from year to year, raising the floor. Constant. And that raised floor is now high enough to support extreme storms outside their traditional window. Constant. The ocean conditions did not just allow Sinlaku to form. Constant. They removed every natural break that should have prevented it from reaching Category 5 intensity. Constant. And when you remove the brakes, the only question is how fast the engine can go. Constant. This is the fuel source, but fuel alone does not explain everything. Constant. Something allowed this storm to ignite. Constant. To go from organised tropical system to a 173-mile-per-hour monster in a shockingly short window. Constant. And that process, rapid intensification, is becoming one of the most dangerous trends in modern meteorology. Constant. Kiran Bhatia and colleagues at Princeton published a 2019 paper in Nature Communications that examined the frequency of rapid intensification events in tropical cyclones globally between 1982 and 2009. Constant. Their finding, corrected for Basin for observational bias for the usual statistical hedges, was that the probability of a tropical cyclone undergoing rapid intensification has increased significantly, especially in the Atlantic, and that the trend is consistent with what climate models predict as ocean temperatures rise. Constant. In plain language, the storms that jump are jumping more often, and they are jumping bigger. Constant. Sinlaku did exactly what that literature predicts. Part 6. The Rapid Intensification Shift. Constant. Super Typhoon Sinlaku did not gradually build its way to peak intensity, it jumped. Constant. Rapid intensification is defined operationally as an increase in maximum sustained winds of at least 35 miles per hour within a 24-hour period. Constant. Sinlaku blew past that benchmark. Constant. The storm underwent a period of explosive deepening that took it from a strong typhoon to a super typhoon in a time frame that challenged operational forecast models to keep up. Constant. By the time updated advisories were issued reflecting the new intensity, the storm had already exceeded the previous forecast ceiling. Constant. This is not a new phenomenon. Rapid intensification has been documented for decades. Constant. But the frequency and magnitude of these events have shifted in ways that the research community has been flagging with increasing alarm. Constant. Studies analysing tropical cyclone data from the 9,980s onward have found that the proportion of storms undergoing rapid intensification has increased significantly. Constant. More storms are making bigger jumps in shorter windows. Constant. And critically, those jumps are happening closer to coastlines, leaving less time between the updated forecast and actual impact. Constant. Think about what that means for warning systems. Constant. The entire emergency preparedness framework, evacuation orders, shelter-in-place directives, resource pre-positioning, hospital surge planning, all of it depends on forecasts issued hours to days in advance. Constant. When a storm intensifies gradually and predictably, forecasters can issue warnings with enough lead time for communities to act. Constant. When a storm rockets from Category 2 to Category 5 overnight, that lead time collapses. Constant. People who went to bed thinking they were facing a manageable storm wake up to a catastrophic one. Constant. And the preparation gap between those two scenarios is enormous. Constant. For the CNMI, this intensification pattern compounds the problem we have already discussed. Constant. These are small, remote islands with limited evacuation options. Constant. You cannot evacuate Tinian the way you evacuate a Gulf Coast city. There are no inland routes. Constant. There is no highway network leading to higher ground in a different state. Constant. Your options are shelter in place or leave by air or sea before the storm arrives. Constant. And both of those options require lead time that rapid intensification eats away. Constant. The overlap between Sinlaiku's rapid intensification and its approach to the Marianas is a case study in exactly the kind of forecasting gap that researchers have been warning about. Constant. The storm outpaced its predictions. Constant. And on islands where the margin for error is already razor thin, where infrastructure is pre-weakened, where resources are limited, where the last disaster was barely recovered from, losing even a few hours of warning time can be the difference between organised preparation and chaos. Constant. This is part of the larger pattern that defines the Sinlaku event. Constant. It is not just that the storm was strong, it is not just that it was slow. Constant. It is that it intensified faster than expected, in a season when it should not have been there at all, over ocean heat that should not have been available, hitting islands that were not ready. Constant. Every variable aligned in the worst direction simultaneously. Constant. There is a specific physical mechanism behind rapid intensification that is worth walking through, because it explains why the warning window is collapsing. Constant. For a tropical cyclone to intensify rapidly, three things need to line up in a very narrow way. Constant. First, ocean heat content deep enough to survive the storm zone mixing, which we already covered. Constant. Second, the storm's inner core has to organise into a compact, symmetric structure. Constant. That means the eye wall convection has to align, the outflow at the top of the storm has to symmetrise, and the mid-level circulation has to stack directly over the low-level centre. Constant. Any wobble, any tilt, any misalignment introduces friction and prevents full efficiency. Constant. Third, the atmospheric environment surrounding the storm has to remove as many obstacles as possible. Constant. That means low wind shear, high moisture, no dry air intrusions from continental sources, and a favourable large-scale flow pattern. Constant. When all three of those conditions align, the storm essentially removes its own brakes, converts thermal energy into kinetic energy at maximum efficiency, and intensifies at rates that push the boundaries of what tropical cyclone theory predicts is possible. Constant. Sinlaku hit all three in April ENSO year. Constant. And that is the piece that keeps coming back at us from every angle. Constant. The alignment was not just favourable, it was optimal. Constant. Kerry Emanuel's theoretical concept of maximum potential intensity, the upper bound of what a tropical cyclone can achieve given its thermodynamic environment, gives you an equation for the ceiling. Constant. That ceiling depends primarily on sea surface temperature, and on the temperature at the top of the storm's outflow layer, which in the tropics is up in the tropopause. Constant. When you plug in the actual measurements from Sinlaku's environment, the maximum potential intensity is right around where Sinlaku actually peaked. Constant. In other words, the storm was not exceeding what physics allowed. Constant. Physics was allowing something that should not have been physically permitted in April, and Sinlaku took the full allowance. Constant. That is the story. The rules did not break. The rules are being written for a different climate. Constant. And speaking of alignment, there is one more atmospheric variable that made all of this possible. Constant. One that opened the door for Sinlaku to reach its full terrifying potential. Part 7. Constant. The wind shear window. Wind shear is the invisible gatekeeper of tropical cyclone intensity. Constant. You can have the warmest ocean on the planet, the most moisture-saturated atmosphere imaginable, and a perfectly organised circulation, and if wind shear is too high, none of it matters. Constant. The storm gets torn apart from the inside. Constant. Wind shear is simply the difference in wind speed or direction between the lower and upper levels of the atmosphere. Constant. When it is high, the top of the storm gets pushed in a different direction than the bottom. Constant. The convective towers, the massive thunderstorm columns that form the engine of the cyclone, get tilted, disrupted, displaced from the centre. Constant energy that should be concentrated around the eye gets spread out. Constant, the storm weakens, or it never strengthens in the first place. Constant, during Sinlaku's critical intensification period, wind shear across the storm environment was measured at approximately 5 to 10 knots. Constant, that is extremely low. Constant. For context, shear values above 2 knots are generally considered hostile to tropical cyclone development. Constant, anything below 10 is considered highly favourable. Constant. Sinlaku was operating in an atmospheric environment that was essentially offering zero resistance to vertical organisation. Constant. With shear that low, the storm's convective structure could stack perfectly. Constant. The circulation at the surface aligned with the circulation aloft. Constant. Outflow channels at the top of the storm remained symmetrical and efficient, venting waste heat cleanly. Constant. The eye wall could contract and intensify without being disrupted by crosswinds at altitude. Constant. Everything lined up. And this is where the compounding nature of this event becomes almost eerie. Constant. None of these individual factors, warm ocean, low shear, high moisture, are unprecedented on their own. Constant. Any given year you can find instances of each. Constant. But finding all of them at this magnitude in this combination in April in the same location at the same time. Constant. That is the piece that makes climatologists uncomfortable. Constant. Because the frequency of these full alignment events, where every favourable condition converges simultaneously, appears to be increasing. Constant. It is the equivalent of rolling dice. Any individual favourable factor is like rolling 1/6. Constant. Not that remarkable, but Sinlaku did not just roll 1/6. Constant. It rolled a 6 on every die at the same table, in a month when most of those dice should not even have been in play. Constant. And when you zoom out and look at tropical cyclone records globally, these perfect alignment events are showing up more often in seasons that used to be quiet, in basins that used to be marginal. Constant. The climate system is not just producing more fuel. Constant. It is producing more opportunities for that fuel to be used at maximum efficiency. Constant. And when one of those opportunities happens to line up with a slow-moving track directly over a populated island chain that is still nursing wounds from the last catastrophe, you get what we are watching right now. Constant. There is a particular structural feature of the atmosphere over the Western Pacific this month that made the low shear window even more remarkable. Constant. The subtropical jet stream, that river of fast-moving air that typically sits at around 200 millibars in the upper atmosphere and steers weather systems across the mid-latitudes, was displaced further north than climatology says it should be for April. Constant. When the jet is in its expected location, its shear influence extends far enough south to disrupt the upper troposphere over the tropical Western Pacific, keeping ambient shear values at 15 to 20 knots. Constant. That is not enough to prevent tropical cyclones outright, but it is usually enough to slow their intensification and cap their peak strength. Constant. With the jet displaced north, that shear influence retreated with it. Constant. The tropical Western Pacific was left with a shear regime more typical of August than April. Constant. And Sinlaku found itself with a genuine open lane. Constant. There was no upper-level enemy trying to knock it down. Constant. The atmosphere effectively cleared the runway. That jet displacement is not random either. Constant. There is a growing body of research on how the mean position of the subtropical jets has shifted poleward over recent decades, a phenomenon documented in multiple analyses of reanalysis data such as the ECMWF's ERA 5 dataset. Constant. As the tropics have warmed and expanded, sometimes described as tropical expansion, the boundaries between the tropical and subtropical circulation regimes have moved further from the equator. Constant. The jets have moved with them. Constant. So the same warming that gave Sinlaku its ocean fuel also, in a sense, opened the shear door by shifting the jet out of the way. Constant. Two independent-looking effects, one root cause, both aligning to produce a single event that violates seasonal expectations. Constant. This is what climate scientists mean when they talk about compounding drivers. Constant. It is not that any single mechanism has become unrecognisably different. Constant. It is that the same warming is producing correlated changes in multiple parts of the system, and those changes are lining up in ways that make certain kinds of extreme events more likely than the old statistics predicted. Constant. But there is one more mechanical factor that has not gotten enough attention. Constant. The same variable I flagged earlier, the one that transforms everything else from dangerous to devastating. Constant. Part 8. The forward speed problem. We need to come back to the 3 knots. Constant. Because it is not just a detail. Constant. It is the variable that multiplies every other threat in this event. Constant. A tropical cyclone's forward speed is controlled by the larger scale atmospheric currents that steer it. Constant. The mid-latitude westerlies, the subtropical ridge, the monsoon trough, the positioning of high and low pressure systems across thousands of miles. Constant. The storm itself generates enormous winds internally, but it moves across the globe at whatever speed the steering flow dictates. Constant. When steering currents are strong and well defined, storms move briskly. Constant. When steering currents are weak, disrupted, or caught between competing influences, storms slow down. Constant. Sometimes to a crawl. Constant. Sinlaku's crawl to 3 knots suggests it was caught in a weakness in the steering pattern, a gap between the subtropical ridge to the north and the equatorial flow to the south, where neither system was assertive enough to push the storm in a clear direction. Constant. The result is a tropical cyclone of extreme intensity essentially drifting, nearly stationary, directly over inhabited islands. Constant. And this is where the Harvey comparison becomes unavoidable again. Constant. When Harvey stalled over Houston, it was not the wind that broke the city, it was time. Constant. Time for the rain to accumulate, time for the bayous to overflow. Constant. Time for the reservoirs to exceed capacity. Time for neighborhoods to go from dry to waist deep. Constant. Sinlaku is doing the same thing on a different scale to a different kind of community. Constant. The islands, the CNMI, do not have Houston's bayou system or reservoir infrastructure. Constant. But they also do not have Houston's drainage capacity, hospital network, or mutual aid agreements with neighboring counties. Constant. What they do have is steep terrain, limited shelter options, and a history of incomplete recovery from previous storms. Constant. The rainfall amplification math is straightforward and brutal. Constant. If Sinlaku were moving at 15 knots, a reasonable speed for a Western Pacific typhoon, any given point on Tinian would experience the heaviest rain bands for perhaps 2 to 3 hours. Constant. At 3 knots, that same point gets 10 to 15 hours of the same rain rates. Constant. The total accumulation does not just increase proportionally. Constant. It overwhelms every absorption and drainage mechanism available, turning rainfall from a hazard into a catastrophe. Constant. The surge tells the same story from a different angle. Constant. Storm surge is driven by the wind pushing water toward the coast. Constant. As long as the wind keeps blowing from the same direction, the water keeps piling up. Constant. A fast-moving storm changes its wind direction relative to any given coastal point over a period of hours, allowing water levels to drop as the geometry shifts. Constant. A slow-moving storm maintains that pressure for far longer. The surge does not recede, it sits. Constant. It infiltrates, it saturates. Constant. And everything at or near sea level that was built to withstand temporary inundation is now dealing with prolonged submersion. Constant. There is a growing body of research suggesting that tropical cyclone forward speeds, on average, have been decreasing in certain basins over the past several decades. Constant. The hypothesis connects this trend to broader changes in atmospheric circulation patterns, specifically a weakening or shifting of the steering currents that guide storms across the ocean. Constant. If that hypothesis holds and the data so far suggests it has merit, then what we are seeing with Sinlaku is not a fluke. Constant. It is a preview of a new class of storm behavior, extreme intensity plus extreme duration. Constant. A combination that our infrastructure, our warning systems, and our recovery frameworks were simply not designed for. Constant duration transforms the hazard type. It takes a windstorm and turns it into a flood event. Constant takes a surge and turns into a coastal reshape. Constant takes a tough night and turns it into a multi-day survival scenario. Constant. And on islands already running a recovery deficit, already patched and patched again, already stretched beyond their fiscal and structural limits, that transformation is existential. Constant. There is one more layer to the forward speed problem that emergency managers talk about privately but rarely in press briefings because it sounds too grim in a headline. Constant. When a storm sits stationary for extended periods, first responder capacity itself erodes during the event. Constant. AMB utility crews cannot pre-stage repairs. Constant. Search and rescue teams cannot enter the affected area until conditions improve. And if conditions do not improve for 10 to 15 hours, the response window that opens after the storm is compressed. Constant. Any injury sustained in hour 2 of the event does not get medical care until hour 12 at the earliest. Constant. Any structural collapse that traps residents in hour 3 does not receive rescue teams until the storm exits. Constant. In a fast-moving storm, the response gap is maybe 3 to 4 hours. Constant. In a slow-moving storm, the response gap can be 8 to 12 hours, sometimes longer. Constant. That is not just an inconvenience. Constant. In medical terms, that is the difference between a survivable injury and a fatality for certain categories of trauma. Constant. In structural terms, that is the difference between rescuing someone from a collapsed building and recovering their body. Constant. Now add something else. Something that happened hours before the storm hit. Constant. Something that has nothing to do with the atmosphere, but everything to do with how humans process overlapping catastrophe. Constant. Part 9. The earthquake hours before impact. Constant. Approximately 6 hours before Super Typhoon Sinlaku's eyewall began crossing the Mariana Islands, a magnitude 5.5 earthquake struck near the Pagan region of the island chain. Constant. The earthquake's focal depth was 219 kilometers, placing it firmly in the category of a deep-focus seismic event. Constant. That depth matters for 2 reasons. First, deep-focus earthquakes in this region are not unusual. Constant. The Mariana Islands sit directly above one of the most active subduction zones on the planet, where the Pacific Plate dives beneath the Philippine Sea Plate. Constant seismic activity is a constant background feature of life in the Marianas. Constant. A magnitude 5.5 at over 200 kilometers of depth would not normally make international news. Constant. Second, and this is the part I need to be very clear about, there is no physical mechanism by which a deep focus earthquake causes or influences a tropical cyclone or vice versa. Constant. The Earth's lithospheric processes and the atmosphere's weather systems operate on fundamentally different energy scales, different time scales, and through different physical media. Constant. The earthquake did not trigger the typhoon did not trigger the earthquake. Constant. They are unrelated events that happen to occur in the same region within the same 12-hour window. Constant. But the human brain is not a seismograph, and it is not a weather model. Constant. The human brain is a pattern detection machine. Constant. And when it sees two rare events converge in the same place at the same time, it connects them, whether the connection is physically real or not. Constant. For residents of the CNMI, already preparing for the most powerful storm to threaten their islands in years, feeling the ground shake 6 hours before the eyewall arrived was not an abstract geological event. Constant. It was psychological compounding. It was the feeling that everything was going wrong at once. Constant. That the universe was stacking threats in a way that felt intentional, even though it was not. Constant. And this is where the earthquake connects to the larger story we are tracking. Constant. Because the feeling of overlapping, escalating disasters is not irrational. Constant. It is just not caused by the specific mechanism people assume. Constant. The earthquake was not linked to the typhoon. Constant. But the pattern of overlapping hazards, natural events stacking on top of each other faster than communities can process and respond, that pattern is real. Constant. It is not supernatural, it is not spiritual. Constant. It is what happens when a system, any system, becomes more energized and more variable. Constant. You get more events, those events distribute randomly in time. Constant. And random distributions produce clusters. Constant. When those clusters land on the same population, the impact is not additive, it is multiplicative. Constant. There is a subtlety here that keeps getting lost in disaster coverage, so let me spell it out. Constant. When two independent hazards hit the same community in the same short time window, the total damage is almost always greater than the sum of what each hazard would have caused alone. Constant. And the reason is that emergency response resources have to be split between the events. Constant. Structural inspections that would have found unsafe buildings after a moderate earthquake never happen because everyone is fighting the storm. Constant. Storm preparation activities that would have secured buildings against wind never happen because the earthquake damaged the shelters where those activities were supposed to be organised. Constant. Communication networks that would have coordinated the response are stressed by two overlapping demand spikes. Constant. The 5.5 earthquake on its own, absent Sinlaku, would have generated a routine geological assessment, some minor property damage inspection, maybe a couple of ambulance calls. Constant. In combination with an inbound Category 5 typhoon, it stripped attention and time from storm preparation at precisely the hours when preparation matters most. Constant. That is compound risk. That is what the emergency management literature calls a cascading disaster. Constant. And the cascading disaster is real, even when the individual events are unrelated in their causation. Constant. There is a specific term researchers use for this kind of overlap, and it is worth introducing. Constant. Multi-hazard event. Constant. The technical definition, drawn from the work of researchers such as Amir Agakochak at the University of California, Irvine, is a scenario in which two or more independent hazards affect the same location or population within a time window short enough that response and recovery efforts cannot proceed independently for each hazard. Constant. Sinlaku plus the pagan earthquake fits that definition perfectly. Constant. Agakochak's 2020 paper in Nature titled Climate Extremes and Compound Hazards in a Warming World walks through the mathematics of why compound events are becoming more common. Constant. As individual hazard frequencies rise, the joint probability of two hazards co-occurring rises even faster, and that is before you consider any actual causal links between them. Constant. Two independent dice, when the individual probabilities go up, the joint probability of both landing in the extreme range simultaneously goes up more than proportionally. Constant. That is basic combinatorics, that is not speculation. Constant. That is exactly what is showing up in the disaster data. Constant. That pattern, that real and measurable increase in overlapping extremes is exactly what was happening across the entire United States on this same day. Constant. Part 10. The US hazard stack. Intensification period, wind shear across the storm environment was measured at approximately 5 to 10 knots. That is extremely low. For context, shear values above 20 knots are generally considered hostile to tropical cyclone development. Anything below 10 is considered highly favourable. Sinlaku was operating in an atmospheric environment that was essentially offering zero resistance to vertical organisation. With shear that low, the storm's convective structure could stack perfectly. The circulation at the surface aligned with the circulation aloft. Outflow channels at the top of the storm remained symmetrical and efficient, venting waste heat cleanly. The eye wall could contract and intensify without being disrupted by crosswinds at altitude. Everything lined up, and this is where the compounding nature of this event becomes almost eerie. None of these individual factors, warm ocean, low shear, high moisture, are unprecedented on their own. Any given year you can find instances of each. But finding all of them at this magnitude in this combination in April in the same location at the same time, that is the piece that makes climatologists uncomfortable. Because the frequency of these full alignment events, where every favourable condition converges simultaneously, appears to be increasing. It is the equivalent of rolling dice. Any individual favourable factor is like rolling 1/6. Not that remarkable, but Sinlaku did not just roll 1/6. It rolled a 6 on every die at the same table in a month when most of those dice should not even have been in play. And when you zoom out and look at tropical cyclone records globally, these perfect alignment events are showing up more often in seasons that used to be quiet, in basins that used to be marginal. The climate system is not just producing more fuel, it is producing more opportunities for that fuel to be used at maximum efficiency. And when one of those opportunities happens to line up with a slow-moving track directly over a populated island chain that is still nursing wounds from the last catastrophe, you get what we are watching right now. There is a particular structural feature of the atmosphere over the Western Pacific this month that made the low shear window even more remarkable. The subtropical jet stream, that river of fast-moving air that typically sits at around 200 millibars in the upper atmosphere and steers weather systems across the mid-latitudes, was displaced further north than climatology says it should be for April. When the jet is in its expected location, its shear influence extends far enough south to disrupt the upper troposphere over the tropical Western Pacific, keeping ambient shear values at 15 to 20 knots. That is not enough to prevent tropical cyclones outright, but it is usually enough to slow their intensification and cap their peak strength. With the jet displaced north, that shear influence retreated with it. The tropical Western Pacific was left with a shear regime more typical of August than April, and Sinlaku found itself with a genuine open lane. There was no upper-level enemy trying to knock it down. The atmosphere effectively cleared the runway. That jet displacement is not random either. There is a growing body of research on how the mean position of the subtropical jets has shifted poleward over recent decades, a phenomenon documented in multiple analyses of reanalysis data such as the ECMWF's ERA5 dataset. As the tropics have warmed and expanded, sometimes described as tropical expansion, the boundaries between the tropical and subtropical circulation regimes have moved further from the equator. The jets have moved with them. So the same warming that gave Sinlaku its ocean fuel also, in a sense, opened the shear door by shifting the jet out of the way. Two independent-looking effects, one root cause, both aligning to produce a single event that violates seasonal expectations. This is what climate scientists mean when they talk about compounding drivers. It is not that any single mechanism has become unrecognisably different. It is that the same warming is producing correlated changes in multiple parts of the system, and those changes are lining up in ways that make certain kinds of extreme events more likely than the old statistics predicted. But there is one more mechanical factor that has not gotten enough attention. The same variable I flagged earlier, the one that transforms everything else from dangerous to devastating. Part 8, the forward speed problem, we need to come back to the 3 knots. Because it is not just a detail. It is the variable that multiplies every other threat in this event. A tropical cyclone's forward speed is controlled by the larger scale atmospheric currents that steer it. The mid-latitude westerlies, the subtropical ridge, the monsoon trough, the positioning of high and low pressure systems across thousands of miles. The storm itself generates enormous winds internally, but it moves across the globe at whatever speed the steering flow dictates. When steering currents are strong and well defined, storms move briskly. When steering currents are weak, disrupted, or caught between competing influences, storms slow down, sometimes to a crawl. Sinlaku's crawl to 3 knots suggests it was caught in a weakness in the steering pattern, a gap between the subtropical ridge to the north and the equatorial flow to the south, where neither system was assertive enough to push the storm in a clear direction. The result is a tropical cyclone of extreme intensity essentially drifting, nearly stationary, directly over inhabited islands. And this is where the Harvey comparison becomes unavoidable again. When Harvey stalled over Houston, it was not the wind that broke the city, it was time. Time for the rain to accumulate, time for the bayous to overflow, time for the reservoirs to exceed capacity, time for neighbourhoods to go from dry to waist deep. Sinlaku is doing the same thing on a different scale to a different kind of community. The islands of the CNMI do not have Houston's bayou system or reservoir infrastructure, but they also do not have Houston's drainage capacity, hospital network, or mutual aid agreements with neighbouring counties. What they do have is steep terrain, limited shelter options, and a history of incomplete recovery from previous storms. The rainfall amplification math is straightforward and brutal. If Sinlaku were moving at 15 knots, a reasonable speed for a Western Pacific typhoon, any given point on Tinian would experience the heaviest rain bands for perhaps 2 to 3 hours. At 3 knots, that same point gets 10 to 15 hours of the same rain rates. The total accumulation does not just increase proportionally, it overwhelms every absorption and drainage mechanism available, turning rainfall from a hazard into a catastrophe. The surge tells the same story from a different angle. Storm surge is driven by the wind pushing water toward the coast. As long as the wind keeps blowing from the same direction, the water keeps piling up. A fast-moving storm changes its wind direction relative to any given coastal point over a period of hours, allowing water levels to drop as the geometry shifts. A slow-moving storm maintains that pressure for far longer. The surge does not recede, it sits, it infiltrates, it saturates. And everything at or near sea level that was built to withstand temporary inundation is now dealing with prolonged submersion. There is a growing body of research suggesting that tropical cyclone forward speeds, on average, have been decreasing in certain basins over the past several decades. The hypothesis connects this trend to broader changes in atmospheric circulation patterns, specifically a weakening or shifting of the steering currents that guide storms across the ocean. If that hypothesis holds, and the data so far suggests it has merit, then what we are seeing with Sinlaku is not a fluke. It is a preview of a new class of storm behaviour, extreme intensity plus extreme duration. A combination that our infrastructure, our warning systems, and our recovery frameworks were simply not designed for. Duration transforms the hazard type. It takes a windstorm and turns it into a flood event. It takes a surge and turns it into a coastal reshape. It takes a tough night and turns it into a multi-day survival scenario. And on islands already running a recovery deficit, already patched and patched again, already stretched beyond their fiscal and structural limits, that transformation is existential. There is one more layer to the forward speed problem that emergency managers talk about privately but rarely in press briefings, because it sounds too grim in a headline. When a storm sits stationary for extended periods, first responder capacity itself erodes during the event. Ambulances cannot travel, utility crews cannot pre-stage repairs. Search and rescue teams cannot enter the affected area until conditions improve, and if conditions do not improve for 10 to 15 hours, the response window that opens after the storm is compressed. Any injury sustained in hour 2 of the event does not get medical care until hour 12 at the earliest. Any structural collapse that traps residents in hour 3 does not receive rescue teams until the storm exits. In a fast-moving storm, the response gap is maybe 3 to 4 hours. In a slow-moving storm, the response gap can be 8 to 12 hours, sometimes longer. That is not just an inconvenience. In medical terms, that is the difference between a survivable injury and a fatality for certain categories of trauma. In structural terms, that is the difference between rescuing someone from a collapsed building and recovering their body. Now add something else, something that happened hours before the storm hit. Something that has nothing to do with the atmosphere, but everything to do with how humans process overlapping catastrophe. Part 9. The earthquake hours before impact. Approximately 6 hours before Super Typhoon Sinlaku's eyewall began crossing the Mariana Islands, a magnitude 5. 5 earthquakes struck near the Pagan region of the island chain. The earthquake's focal depth was 219 kilometers, placing it firmly in the category of a deep focus seismic event. That depth matters for 2 reasons. First, deep focus earthquakes in this region are not unusual. The Mariana Islands sit directly above one of the most active subduction zones on the planet, where the Pacific Plate dives beneath the Philippine Sea Plate. Seismic activity is a constant background feature of life in the Marianas, a magnitude 5. 5 at over 200 kilometers of depth would not normally make international news. Second, and this is the part I need to be very clear about, there is no physical mechanism by which a deep-focused earthquake causes or influences a tropical cyclone, or vice versa. The Earth's lithospheric processes and the atmosphere's weather systems operate on fundamentally different energy scales, different timescales, and through different physical media. The earthquake did not trigger the typhoon did not trigger the earthquake. They are unrelated events that happen to occur in the same region within the same 12-hour window. But the human brain is not a seismograph, and it is not a weather model. The human brain is a pattern detection machine, and when it sees 2 rare events converge in the same place at the same time, it connects them, whether the connection is physically real or not. For residents of the CNMI, already preparing for the most powerful storm to threaten their islands in years, feeling the ground shake 6 hours before the eyewall arrived was not an abstract geological event. It was psychological compounding. It was the feeling that everything was going wrong at once, that the universe was stacking threats in a way that felt intentional, even though it was not. And this is where the earthquake connects to the larger story we are tracking, because the feeling of overlapping, escalating disasters is not irrational. It is just not caused by the specific mechanism people assume. The earthquake was not linked to the typhoon, but the pattern of overlapping hazards, natural events stacking on top of each other faster than communities can process and respond, that pattern is real. It is not supernatural, it is not conspiratorial. It is what happens when a system, any system, becomes more energized and more variable. You get more events. Those events distribute randomly in time, and random distributions produce clusters. When those clusters land on the same population, the impact is not additive, it is multiplicative. There is a subtlety here that keeps getting lost in disaster coverage, so let me spell it out. When two independent hazards hit the same community in the same short time window, the total damage is almost always greater than the sum of what each hazard would have caused alone. And the reason is that emergency response resources have to be split between the events. Structural inspections that would have found unsafe buildings after a moderate earthquake never happen because everyone is fighting the storm. Storm preparation activities that would have secured buildings against wind never happen because the earthquake damaged the shelters where those activities were supposed to be organised. Communication networks that would have coordinated the response are stressed by two overlapping demand spikes. The 5 earthquake on its own, absent Sinlaku, would have generated a routine geological assessment, some minor property damage inspection, maybe a couple of ambulance calls. In combination with an inbound Category 5 typhoon, it stripped attention and time from storm preparation at precisely the hours when preparation matters most. That is compound risk. That is what the emergency management literature calls a cascading disaster. And the cascading disaster is real, even when the individual events are unrelated in their causation. There is a specific term researchers use for this kind of overlap, and it is worth introducing: multi-hazard event. The technical definition, drawn from the work of researchers such as Amir Agakochak at the University of California, Irvine, is a scenario in which two or more independent hazards affect the same location or population within a time window short enough that response and recovery efforts cannot proceed independently for each hazard. Sinlaku plus the pagan earthquake fits that definition perfectly. Agakuchak's 2020 paper in Nature, titled "Climate Extremes and Compound Hazards in a Warming World," walks through the mathematics of why compound events are becoming more common. As individual hazard frequencies rise, the joint probability of two hazards co-occurring rises even faster, and that is before you consider any actual causal links between them. Two independent dice. When the individual probabilities go up, the joint probability of both landing in the extreme range simultaneously goes up more than proportionally. That is basic combinatorics, that is not speculation. That is exactly what is showing up in the disaster data. That pattern, that real and measurable increase in overlapping extremes, is exactly what was happening across the entire United States on this same day. Part 10, the US hazard stack. While Sinlaku was grinding across the Mariana Islands, the continental United States was simultaneously experiencing its own cascade of extreme events. And the simultaneity is the point. Because every one of these events taken individually would be significant. Taken together on the same day, they paint a picture of a system running hot. Across the mid-Atlantic, temperatures were approaching or breaking all-time April records. Stations from Washington, D.C. to Philadelphia were reporting readings 15 to 30 degrees Fahrenheit above normal for mid-April. These are not the kind of departures that get filed under warm day. These are departures that belong to a different season entirely. People were experiencing late June heat in mid-April. And the records being challenged were not recent, soft records. Some of them had stood for decades. Simultaneously, the Storm Prediction Center had issued an enhanced risk for severe weather across Iowa and the Great Lakes region. An enhanced risk is the third tier on a 5-tier scale, meaning the forecasters were confident in the potential for significant severe thunderstorms, including tornadoes, large hail, and damaging wind gusts. This risk area covered millions of people across multiple states. And the setup was driven in part by the same anomalous warmth that was breaking records further east. Warm, moist air surging northward, colliding with a jet stream disturbance. At the same time, 13 red flag warnings were active across the high plains. Red flag warnings mean that conditions are ideal for wildfire ignition and rapid spread. Low humidity, high winds, dry vegetation. 13 simultaneous warnings across a single region represent a significant fire weather event, tying up resources and attention across multiple states. Flooding was already underway in parts of Michigan and Wisconsin, where persistent rainfall had saturated soils and pushed rivers over their banks. Step back and look at this from the perspective of national emergency management. On one single day, the United States had a super typhoon striking an inhabited territory, record heat across a major population corridor, tornado risk across the Midwest, critical fire weather across the plains, active flooding in the Great Lakes region. The National Weather Service had issued more than 300 active warnings, watches, and advisories simultaneously across the country. 303 to be exact. Now, every one of these events has its own proximate cause. The heat is driven by a specific atmospheric ridge pattern. The severe weather is driven by a specific frontal boundary and jet configuration. The fire weather is a product of seasonal dryness and wind. None of them are directly connected to each other in any simple causal chain, but they are all occurring within the same climate system, and that system's baseline has shifted. Warmer average temperatures mean more energy in the atmosphere. More energy means more moisture transport, stronger temperature contrasts, more intense heat events, more vigorous storm dynamics. The dice are not loaded in favour of any single event. They are loaded in favour of more events, period. And when you roll loaded dice enough times, you get days like this, where the map lights up from coast to coast and the emergency management system has to triage at the national scale. There is something worth noticing about the specific configuration on this day, because it is not random. It is not just a scatter of unrelated bad weather. The heat dome over the eastern seaboard was being driven by an anomalously strong upper-level ridge, a big bulge of high pressure aloft that was compressing and warming the air beneath it. The severe weather setup over the Midwest was being driven by the interaction between that same ridge and a cut-off upper-level low that was displacing the jet stream in an unusual way. The fire weather in the plains was being driven by the strong downslope flow off the Rockies induced by the pressure gradient between the ridge and that upper low. In other words, one large-scale atmospheric pattern, a highly amplified Rossby wave configuration in the Northern Hemisphere jet stream, was simultaneously producing the heat, the storms, the fire weather and the flooding by acting on different geographic pieces of the country in different ways. This is not 4 unrelated events. It is one weather pattern producing 4 different regional expressions of the same underlying setup. There is a paper by Kai Kornhuber and colleagues from 2019 in Nature Climate Change, Extreme Weather Events in Early Summer 2018 Connected by a Recurrent Hemispheric Wave 7 Pattern, that documented exactly this kind of multi-region simultaneous extreme event and connected it to what atmospheric scientists call quasi-resonant amplification of planetary waves. In a warming world, the theory goes, the jet stream sometimes locks into patterns where its meanders become larger and more stationary than they used to be. When that happens, the same regions get baked or flooded or scorched or shaken by storms for days in a row, and multiple regions can be locked into different extremes at the same time under the same wave pattern. That is exactly what this day looks like. This is what the central thread of this story looks like from 30,000 feet. It is not one storm, it is not one heat wave. It is an entire system producing overlapping extremes faster than the response infrastructure can keep up. Sinlaku is the most dramatic single event on this particular day, but it is part of a mosaic. And that mosaic is getting more complex with each passing year. And just to put one more frame around how surreal this particular 24-hour window was, while all of this was unfolding on the ground and in the atmosphere, something was happening overhead that added one more layer to an already overloaded day. Part 11, the asteroid pass. An asteroid pass within zero. 68 lunar distances of Earth during the same approximate window. That is roughly 165,000 miles, or about 2/3 of the distance from here to the Moon. It was harmless. The trajectory was well tracked, well understood, and posed zero impact risk. Astronomers had catalogued it, calculated its orbit with precision, and confirmed it would pass cleanly. In any other news cycle, it would have been a minor science item, maybe a paragraph in a space enthusiast newsletter. But on a day when a super typhoon was destroying American territory, an earthquake had rattled the same island chain hours earlier, the continental U.S. was burning and flooding and baking and tornado warned simultaneously, and more than 300 emergency alerts were active from coast to coast. An asteroid buzzing past inside the Moon's orbit felt like a punchline the universe was writing in real time. Not because it was dangerous, but because the human brain has a threshold for simultaneous anomalies, and this day had blown past it. Here is what the asteroid actually was in operational terms. It was a small near-Earth object, likely somewhere between 20 and 50 meters in diameter, tracked and characterized by the Minor Planet Center and confirmed by follow-up observations at multiple observatories. Objects of this size class pass at these distances a few times a year on average. Sometimes the pass is closer, sometimes further. The famous 2013 Chelyabinsk event, an object roughly 20 meters across that exploded over Russia and injured over 1,500 people, was smaller than this one. If this asteroid had entered the atmosphere, it would have been a significant event, but it did not. Its orbit brought it near Earth and then swept it back out into the solar system, exactly as calculated. The reason it did not enter the atmosphere is simple. Its orbital path, defined by celestial mechanics that have been in play for billions of years, does not intersect Earth's orbit at a point where Earth actually is when the asteroid gets there. Trajectory is destiny in orbital mechanics, and this trajectory did not include an impact. But there is something worth thinking about here that goes beyond this single asteroid. NASA's Planetary Defense Coordination Office and the international network of survey telescopes have gotten dramatically better at finding these objects over the last decade. Missions like NEOEYE's Pan-STARRS and the Catalina Sky Survey now catalogue thousands of near-Earth objects per year. The Vera Rubin Observatory in Chile, once fully operational, is expected to discover more near-Earth objects in its first year than the entire cumulative catalogue of previous decades. That is a good thing. Better detection means better warning. Better warning means better response options. The 2022 DART mission, which deliberately crashed a spacecraft into the asteroid Dimorphos to test whether we could nudge a hypothetical Earth-threatening object off course, produced results that were more successful than most simulations predicted. In other words, we now have empirical evidence that a kinetic impactor can meaningfully alter the trajectory of a small asteroid. We are, for the first time in the history of our species, developing an actual planetary defense capability. This particular asteroid did not need it. But the fact that we knew about it, tracked it, and had contingency options if it had needed intervention is a genuine achievement that most people do not stop to acknowledge, because the news cycle never gives credit for a disaster that did not happen. The asteroid is not part of the climate story, but it is part of the perception story. And on a day defined by overlapping extremes, perception matters. Because perception drives public response, media narrative, and political will. When everything seems to be happening at once, people either wake up or shut down. Both reactions have consequences. If they wake up, they demand action, they support preparedness funding, they take individual measures to reduce their own vulnerability. If they shut down, they disengage from information, they dismiss warnings, they let the next disaster hit them unprepared because they have already exhausted their attention budget on the current one. The asteroid on Sinlaku Day was a coincidence, but the way that coincidence lands in the public consciousness, whether it produces engaged responses or exhausted disengagement, has real consequences for how the next real threat is met. And there will be a next real threat. Statistically, there always is. Part 12. 303 warnings nationwide. 303. That was the number of active warnings, watches and advisories simultaneously issued across the United States on this day. Flood warnings, tornado watches, fire weather alerts, extreme wind warnings, marine warning, heat advisories, surf advisory. The full spectrum of atmospheric hazard lit up coast to coast all at the same time. That number is not just a headline, it is a stress test result. The National Weather Service, FEMA, state emergency management agencies, county-level first responders. All of these systems are designed with capacity assumptions baked in. They are built to handle a certain volume of simultaneous events. When you have a hurricane in the Gulf and a severe weather outbreak in the plains at the same time, the system stretches but holds. Resources shift, mutual aid agreements activate, personnel deploy from quiet regions to active ones. But 303 active alerts means there are very few quiet regions left to draw from. Every pocket of the country is dealing with something. The fire crews in Kansas cannot be sent to assist with flooding in Michigan because Kansas has its own emergency underway. The search and rescue assets that might normally be pre-positioned for a Pacific typhoon response have to weigh that against the tornado risk bearing down on Des Moines. The system is not designed for everywhere to be on fire, figuratively or literally, at the same time. There is a phrase that risk analysts use, alert saturation. It describes the point at which the volume of warnings exceeds the public's ability to process and respond to them. When your phone buzzes with a tornado warning while you are still reading the heat advisory that came in an hour ago, and the news is showing footage of a typhoon hitting an American territory you may not have heard of, the cognitive load becomes overwhelming. People stop reading the alerts, they stop taking action. The warning system, no matter how accurate, loses its effectiveness because the audience is maxed out. That is the invisible hazard of a day like this. It is not just that the storms are dangerous. It is that the sheer volume of simultaneous danger degrades the ability of both institutions and individuals to respond to any single threat effectively. The system is being tested at a level it was not designed for, and the strain shows up in delayed responses, missed evacuations, and communities that fall through the cracks because attention and resources have been pulled in too many directions at once. There is a specific research finding that quantifies alert saturation, and I want to share it because it changes how you understand this problem. Studies of wireless emergency alert response, the little textile alerts your phone gets from local authorities, have consistently shown that response rates to any individual alert drop when the recipient has received other alerts within the previous 24 to 48 hours. The drop is not small. In some studies, second and third alerts within a short window see response rates 30 to 50% lower than the first alert. That is the size of the alert saturation effect, and it is measured, it is not a hypothesis. When you flood the same population with multiple warnings across multiple hazards, each additional warning is genuinely less effective than the last. Emergency managers know this. They try to prioritize the most life-threatening alerts. They try to avoid crying wolf on borderline events. They try to design messaging that stands out even in a saturated environment. But there are limits, and a day with 303 simultaneous warnings pushes past those limits. There is another wrinkle here, one that emergency managers rarely discuss openly but that shows up in every after-action report. When alerts saturate, individual behaviour shifts in predictable ways. Some people over-respond, evacuating for events that do not require it, clogging highways, occupying shelter space that other people needed more. Some people under-respond, ignoring even legitimate life-threatening warnings because they have decided the system is crying wolf. Both patterns cause harm. The over-responders can prevent the highest-risk populations from evacuating in time. The under-responders become the fatalities the response system was designed to prevent, and the system as a whole has no good way to correct for either failure mode in real time. You cannot tell the person driving away from a Category 1 tropical storm they should have stayed home. You cannot tell the person who ignored the extreme wind warning in Saipan that they should have listened before the eye wall arrived, because if they did not listen, they may not be alive to hear the correction. And all of this circles back to the same pattern. Compressed recovery windows, a climate system producing more events more often with less breathing room in between. Sinlaku is not an isolated catastrophe. It is one node in a network of simultaneous stress that stretches from the Western Pacific to the Eastern Seaboard. The question now is whether this particular day is an anomaly, a once-in-a-generation pile-up of bad luck, or whether it is something else entirely. Part 13. The April Problem. April is supposed to be quiet in the Western Pacific tropical cyclone record. April sits at the bottom of the activity charts. The accumulated cyclone energy for the month, averaged over decades, barely registers compared to the August through November peak. Most years April passes without a single named storm in the basin. A weak tropical depression might form and dissipate without reaching typhoon strength. That is normal, that is expected. Super typhoon at 173 miles per hour is not normal, it is not expected. And it is not without precedent, but the precedents are so rare they barely qualify as a category. Typhoon Hester in 9,966 remains one of the only documented cases of a super typhoon strength storm forming in late March or early April. Hester peaked as a Category 5 equivalent in early April of that year, an event so unusual that it was treated as a meteorological curiosity, interesting for textbooks, not particularly relevant for operational planning. The assumption was that Hester-type events represented the extreme tail of the distribution, events with return periods measured in many decades. Sinlaku challenges that assumption directly. 60 years later, another super typhoon of comparable intensity in April. 2 data points do not make a trend in a strict statistical sense, but they do constrain the probability space. If events like this had a true return period of, say, 100 years, having 2 occur within 60 years is unlikely but possible. If the return period was 50 years, it is less surprising. And if the underlying conditions are shifting, if the baseline ocean temperature is higher, if the warm pool extends earlier in the year, if wind shear patterns are more frequently favourable in spring, then the effective return period might be decreasing over time, making April super typhoons not just possible, but increasingly probable. This is what meteorologists mean when they talk about season creep. The boundaries that used to define hurricane and typhoon seasons were never hard lines. Nature does not operate on a calendar, but they were reasonably reliable statistical boundaries. You could plan around them. Insurance actuaries built models based on them. Building codes referenced them. Emergency management timelines were structured around them. When those boundaries start to shift, when the season effectively starts earlier and ends later, everything downstream has to be recalibrated. Recalibration takes time and political will, 2 resources that tend to be in short supply. The warmer baseline ocean temperatures we discussed earlier are not just fuel for individual storms. They are the mechanism by which the season itself expands. If the ocean reaches the thermal threshold for cyclone development a month earlier than it used to, then the window during which extreme storms are possible widens by a month. Multiply that across decades and you get a world where April super typhoons are not outliers, they are early entries in a season that functionally never quite ends. There is a specific piece of data from the Atlantic Basin worth mentioning here because it illustrates the trend even more starkly. Between 1965 and 2010, the average first-named storm of the Atlantic hurricane season formed in early to mid-June. Between 2015 and 2025, the average first-named storm has been forming in mid to late May, and in several individual years the first-named storm formed in April, or even in one case in the previous November's storm being renamed. The National Hurricane Center formally changed its issuance of the routine Atlantic tropical weather outlooks to begin on May 15 instead of June 1 in acknowledgement of this shift. That is not a subtle change. That is the National Forecast Agency officially recognizing that the season now starts 2 weeks earlier than the historical definition indicated. Similar reviews are ongoing for other basins. The Western Pacific has always been a nominally year-round basin in theory, but with a strong seasonal peak in practice. If the seasonal peak is beginning to broaden, if April can now produce a Sinlaku, then the operational planning assumptions for the CNMI, for Guam, for the Philippines, for Taiwan, for Japan, all have to be re-examined. And that re-examination is happening, slowly, unevenly, and always in the aftermath of an event that could have been anticipated if the assumptions had been updated sooner. There is also a policy dimension to season creep that deserves attention. Federal disaster assistance under the Stafford Act, the primary legal framework for FEMA response in the United States, does not have a seasonal boundary written into it. The President can declare a disaster in any month based on the severity of the event. But the operational readiness of federal response resources, the pre-positioning of supplies, the seasonal hiring cycles for emergency contractors, the maintenance schedules for aircraft and vessels, all of these are calibrated around the historical seasonal expectation. When a super typhoon hits in April, some of those systems are simply not in their peak readiness posture. The trucks are still in maintenance, the temporary hires have not been onboarded yet. The staging areas have not been fully stocked. Everything can be surged, and it will be, but the ramp-up time comes out of the response window. In practical terms, that means slower initial response, longer waits for essential supplies, and more strain on the local resources that are supposed to bridge the gap until federal assistance fully arrives. And if this is what the expanded season produces in its margins, a 173-mile-per-hour monster hovering over you. S territory? What does the peak look like? Part 14. ENSO does not explain this. Here is the thing that should bother anyone looking for a simple explanation. The El Niño Southern Oscillation, ENSO, the single most influential mode of natural climate variability on Earth, the cycle that modulates tropical cyclone activity across every ocean basin, the go-to explanatory framework for any unusual storm season, is essentially neutral right now. The ENSO index at the time of Sinlaku's formation was approximately positive 0.16. That is effectively zero. Not El Niño, not La Niña, neutral. The Pacific Ocean is not in an anomalous ENSO state. It is sitting in the middle of the road doing absolutely nothing remarkable. And that paradoxically is the most remarkable part of this entire story. Under normal circumstances, a neutral ENSO year produces moderate tropical cyclone activity in the Western Pacific. Not suppressed, not enhanced, moderate. The atmospheric conditions that drive cyclone formation and intensification are neither boosted nor inhibited by ENSO teleconnections. You would expect a roughly average number of storms with roughly average intensities occurring during the roughly normal seasonal window. That is what the textbook says. That is what the models predict. That is what decades of operational forecasting have been built on. The assumption that ENSO state tells you more than any other single variable what kind of storm season to expect. What you would not expect, what no ENSO-based seasonal forecast would predict, is a 173-mile-per-hour super typhoon making landfall on you. S territory in April. That is not a moderate activity event. That is not even a high activity event. That is an extreme out-of-season, record-challenging event occurring in the complete absence of any identifiable large-scale climate mode that would explain it. It is like watching someone throw a 98-mile-per-hour fastball and then being told they are not even a pitcher. They are not supposed to be able to do this. And yet, here we are, watching the radar loop. Now, if Sinlaku had formed during a strong El Niño year, we would have a tidy explanation. El Niño shifts the tropical convection eastward in the Pacific, expands the warm pool, reduces wind shear across the Western Pacific development region, and generally juices the conditions for tropical cyclone formation and intensification. You could point to the ENSO state and say that is why. The models would have seen it coming. The seasonal forecast would have flagged elevated risk. The event would have been unusual because of its timing, but the intensity would have had a plausible driver that everyone could agree on. The explanation would fit the framework, but the framework is not cooperating this time. ENSO is neutral. The big lever that is supposed to explain the big events is not being pulled. And that absence of explanation is, itself, a kind of explanation, if you are willing to look at what it implies. This mismatch between the expected ENSO state and the observed event is significant because it points to something else going on beneath the ENSO signal. Something that does not oscillate, something that does not cycle back. ENSO operates on top of a baseline. It modulates activity up and down around whatever the average state happens to be. It is a wave superimposed on a level surface. But if the surface itself is tilting, if the baseline ocean temperature is higher, if the atmospheric moisture content is greater, if the conditions favourable for tropical cyclone development are more broadly present across more of the ocean for more months of the year, then even a neutral ENSO year can produce events that would have been considered extreme under the old baseline. Let me put that in a way that sticks. Think of ENSO like a thermostat in a house. It cycles the temperature up and down around a set point. El Niño turns the heat up. La Niña brings it down. Neutral sits in the middle. And for decades, that thermostat was the thing we watched. If the house felt warm, we checked the thermostat. If there was a bad storm season, we asked what ENSO was doing. It was the first variable and usually the most important one. But someone has been gradually turning the set point higher, not the thermostat, the set point itself, the baseline around which the thermostat oscillates. So now when ENSO cycles down to its neutral position, which should feel like the middle of the road, the house is already warmer than it used to be during the old El Niño peaks. The oscillation is doing exactly what it has always done. The floor underneath it has risen. And when the floor rises high enough, you do not need El Niño to produce extreme events anymore. The neutral state is sufficient. The middle of the road is now where the edge of the road used to be. That is what Sinlaku is showing us. Not that ENSO is broken, ENSO is working fine. It is doing exactly what it does. The problem is that the system it is oscillating within has shifted to a state where normal is enough to power a Category 5 super typhoon in April. The thermostat is cycling correctly, the house is just hotter. Researchers have been tracking this signal for years, and while there is appropriate scientific caution about attributing any single event to long-term trends, because single events are inherently noisy, and you need statistical aggregation to distinguish signal from noise, the pattern in the data is getting harder to attribute to chance alone. Extreme tropical cyclone events are increasingly occurring outside the conditions that traditionally explained them. They are happening in neutral ENSO years, in off-peak months, in ocean basins and sub-regions that were not historically prone to them. The traditional frameworks still work as relative modulators. El Niño years still tend to produce more Pacific cyclones than La Niña years, and La Niña years still tend to boost Atlantic activity. The dials still turn in the expected direction. But the absolute thresholds keep getting exceeded regardless of where the dial is pointed. You get a record-breaking Atlantic season during a La Niña year when La Niña is supposed to suppress Atlantic activity. You get a super typhoon in April during neutral ENSO, when April is not supposed to produce super typhoons under any ENSO state. The relative patterns hold. The absolute outcomes are drifting outside the envelope. And here is what I keep coming back to when I look at events like this. If the baseline keeps rising, and every major ocean heat dataset says it is, then we are entering a period where the traditional predictive frameworks become progressively less useful. Not because they are wrong about the relative effects of ENSO, but because they are calibrated to absolute thresholds that no longer match reality. A model that says neutral ENSO equals moderate cyclone activity is technically correct about the ENSO relationship. But if moderate now includes April super typhoons, the word has lost its meaning. The model is not lying to you, it is just speaking a language that was defined in a cooler world. Sinlaku in April, under neutral conditions, over ocean heat that should not be there yet, with rapid intensification that outpaced the models, moving at a speed that maximizes destruction. This is one more data point in a growing collection of events that the old explanatory frameworks struggle to account for. And that should matter to everyone. Not just meteorologists and climate scientists, but emergency managers, insurance actuaries, infrastructure planners, and the communities living in harm's way. Because our forecasting systems, our preparedness protocols, our building codes, and our risk models are all calibrated to those old frameworks. They are calibrated to the old set point. They assume the floor is where it used to be. When reality starts consistently exceeding the models need updating. And until they are updated, communities remain exposed to risks they are not being adequately warned about. People make decisions based on what the models tell them. If the models say April is a low-risk month, people do not prepare for a Category 5. If the forecast says neutral ENSO means moderate activity, governments do not pre-position resources for an extreme event. The gap between model output and observed reality is not an academic problem. It is a survival problem, measured in evacuation orders that come too late and in shelters that were not open. The question then is not what caused this storm. The physics are clear. Warm ocean, low shear, favourable moisture, weak steering currents. We have walked through every variable. The question is how often the conditions for storms like this will align. How frequently the new baseline will be sufficient to produce events that used to require the extra push of El Niño. How many more April super typhoons? How many more neutral year extremes? How many more model-exceeding outcomes will it take before the frameworks are recalibrated and the preparedness posture catches up? And to answer that, you have to look at the timeline. Part 15, The Rebuild Gap, U2 2018, Moir 2026, 3 names, 8 years. And if you line them up on a timeline, just mark the dates, nothing else, a pattern emerges that has nothing to do with meteorology and everything to do with mathematics. The average interval between major cyclone events hitting the Commonwealth of the Northern Mariana Islands has compressed from decades to years. Not gradually, not over some long ambiguous period where you could argue about the trend. In the span of a single generation of residents, the gap between catastrophic storms has gone from something you might experience once or twice in a lifetime to something you now brace for every few years. And here is the other side of that equation, the side that makes the math truly devastating. The recovery duration required after each event has not compressed at all. If anything, it has lengthened because each successive storm degrades the very capacity, fiscal, structural, institutional needed to manage recovery. The storms are coming faster, the rebuilding is taking longer, and those two trend lines are moving in opposite directions, which means at some point they cross. And when they cross, recovery as a concept becomes meaningless, because you never finish before the next one arrives. Let me walk you through what that looks like in practice, because the abstraction hides the human reality. After Super Typhoon Yutu in 2018, a storm that struck Tinian and Saipan with sustained winds of 180 miles per hour, the strongest tropical cyclone to ever make landfall on U.S. soil, the CNMI faced a reconstruction effort measured in years and hundreds of millions of dollars. Federal disaster declarations were issued. FEMA deployed personnel and resources across the Pacific. Supplemental appropriations were requested from Congress to cover costs that the territory's own budget could not begin to absorb. The machinery of federal disaster response activated, and to its credit it delivered real assistance, but the recovery process was slow, not because of negligence or incompetence, but because of the fundamental realities of rebuilding a remote island territory in the middle of the Pacific Ocean. Contractor availability was limited. You cannot just drive a construction crew to Tinian the way you drive into a hurricane-damaged town in Florida. Materials had to be shipped across thousands of miles of open water. Supply chains that were already strained by global logistics issues became bottlenecks. Skilled labour had to be imported and housed on islands whose housing stock had just been destroyed. Every step of the process took longer and cost more than it would have on the mainland. 3 years after Yutu, significant reconstruction work was still ongoing. The power system had been partially restored, but full hardening, the kind of infrastructure investment that would make the grid resilient to the next major storm, was incomplete. Housing stock remained below pre-storm quality. Many residents were living in structures that had been patched and repaired, but not rebuilt to modern typhoon-resistant standards. Public infrastructure, schools, medical facilities, government buildings was functional. But the word functional was doing a lot of heavy lifting in that assessment. Functional meant the lights were on and the doors opened. It did not mean the buildings could withstand another direct hit from a Category 5 storm. And then Mawar came through in 2023, another storm. Another round of damage to systems that had not finished being rebuilt from the last time. Think about what that means for the people living through it. You spend 3, 4, 5 years watching your community slowly put itself back together. The roof gets fixed, the school reopens, the power stays on for weeks at a time without interruption. Things start to feel almost normal again, and then the satellite imagery lights up. The forecast track draws a line directly over your island, and you realise you are about to go through the entire cycle again. Except this time the starting point is worse. The buildings are weaker, the budget is smaller, the will is more fragile, the recovery timeline resets, but it resets from a lower starting point. Each reset begins from a deficit that the previous recovery never fully closed. It is like trying to fill a bathtub while someone keeps pulling the plug at shorter and shorter intervals. You never quite reach the level you had before, and each time the water drains, it takes a little more of the enamel with it. Now Sinlaku in 2026, 8 years after Yutu, 3 years after Mawar, and the islands are again absorbing a catastrophic cyclone with infrastructure that reflects not just the current storm's damage, but the accumulated, compounded, layered damage of every storm that came before it, and every recovery that fell short of completion. The concrete that is cracking under Sinlaku's winds was not poured fresh, it was patched after Yutu, patched again after Mawar, and is now taking 173 mile/hour gusts with the structural integrity of a wall that has been broken and glued back together twice. The question that disaster researchers and policy planners are increasingly confronting, and it is a question that does not have a comfortable answer, is whether this cycle is sustainable, not whether the islands can survive any individual storm. They have survived them repeatedly at enormous human cost and with extraordinary resilience. The people of the CNMI are not fragile, they have endured things that would break most communities. The question is whether the accelerating frequency of these events permits meaningful recovery at all, whether recovery as a goal is even achievable when the next disaster arrives before the last one's damage is repaired. There is a point at which the recovery gap becomes structural, not a temporary funding shortfall that a supplemental appropriation can fix. Not a logistical delay that better planning can shorten, a permanent condition in which the community exists in a state of perpetual partial recovery. Infrastructure is always somewhat degraded. Housing quality is always below what codes require for new construction. The power grid is always one bad storm away from collapse because the upgrades that would prevent collapse were never finished before the last bad storm arrived. The economic base is always operating under storm debt. Money that should be going to development, education, healthcare and quality of life, instead being redirected to repair again. The social fabric is always strained by displacement, by uncertainty, by the psychological weight of knowing that the next event is not a question of if but when. And when is getting closer with every cycle. I want you to sit with that for a moment. Because this is not happening in some abstract, faraway place. This is an American community. These are US citizens. They carry American passports, pay into the same federal systems, and are supposed to receive the same federal protections as someone living in Miami or Houston or San Juan. And they are trapped in a cycle of destruction and incomplete recovery that is accelerating beyond their ability, beyond anyone's ability, to manage with current resources and current frameworks. The CNMI is not the only community facing this reality. Across the Pacific, small island nations are watching the same math play out on their own shores. Across the Caribbean, communities that were devastated by Maria in 2017 and Irma the same year are still rebuilding, still carrying the scars, still watching each new hurricane season with the knowledge that their infrastructure is not ready for another direct hit. Along coastlines worldwide, the same pattern is emerging. Storm recurrence is outpacing recovery capacity. The interval between disasters is shrinking. The time needed to rebuild is not. And the gap between those timelines is where communities get ground down. But the CNMI as a U.S. territory occupies a unique and uncomfortable position in this story. The federal government bears a constitutional and moral obligation to the safety and recovery of its citizens in the Northern Marianas. FEMA has a mandate, Congress has the authority to appropriate funds. The Department of Defense has assets in the region. The institutional capacity exists, at least on paper, to mount a recovery effort commensurate with the need. And yet, the federal response infrastructure, while formidable, is increasingly being asked to respond to overlapping disasters simultaneously. This is exactly the scenario that 303 active warnings on a single day illustrates. When the entire country is dealing with extreme weather at the same time, when there are fires in the plains and floods in the Great Lakes, and tornadoes in the Midwest, and a super typhoon in the Pacific, the resources have to be divided. The attention has to be shared. And historically, remote territories with small populations and no electoral votes do not win the competition for attention when the mainland is also hurting. That is not cynicism, that is pattern recognition from every previous disaster cycle. The rebuild gap is not a future risk, it is a present reality. It is playing out right now, on islands currently being pounded by the strongest storm on Earth. Islands that were still patching the damage from the last storm, which hit before the damage from the storm before that was fully repaired. It is a ratchet that only turns one direction. And with every click, the community drops a little lower, the baseline degrades a little further, and the distance between where they are and where they need to be to withstand the next event grows a little wider. And it is widening. Part 16. Cluster illusion versus reality. At this point in the story, the natural question is obvious, and I would be surprised if you were not already asking it. Are disasters actually getting worse, or does it just feel that way? It is a fair question. It might be the most important question you can ask right now, and the honest answer is, it is both. And the fact that it is both is exactly what makes this so difficult to navigate. Because the human brain is not well equipped to hold two contradictory truths at the same time and give each one its proper weight. Human beings are hardwired for pattern detection. It is one of our greatest cognitive strengths. It is the reason we survived as a species. The ability to see a rustle in the grass and infer a predator. To notice a change in the sky and predict a storm. To connect two events and extract a rule that keeps us alive. Pattern detection is the foundation of science, of medicine, of engineering, of every system we have ever built to understand and control our environment. It is, without exaggeration, one of the most powerful tools evolution has ever produced. It is also one of our most reliable cognitive traps. We see 2 or 3 unusual events close together in time, and we instinctively construct a narrative connecting them. The earthquake 6 hours before the typhoon, those must be related. The heat wave on the East Coast happening the same day as a tornado outbreak in the Midwest, that cannot be a coincidence. The asteroid passing overhead while the map lights up with 300 warnings, something is going on. Our brains take these coincidences and weave them into a story of escalation. A feeling that things are spiraling, that invisible forces are converging, that the system is breaking down in real time, and everything is connected to everything else. That feeling is powerful, it is visceral, and it is not entirely wrong. But it is not entirely right either. And the gap between those two things is where a lot of confusion and a lot of bad decision-making lives. In statistics, this tendency has a name, the clustering illusion, and understanding it is essential to making sense of a day like today without either panicking beyond what the evidence supports or dismissing real signals because they are tangled up with noise. Random events distributed in time do not distribute evenly, they clump. This is not intuitive because when most people imagine randomness, they imagine an even spread. Events spaced out at regular intervals, like fence posts along a highway. But real randomness does not look like that. Real randomness is lumpy. A Poisson distribution, the mathematical model used to describe the timing of random independent events, predicts that clusters will occur purely by chance. Not might occur, will occur. Some years will have more events than average, some will have fewer. And the variation itself is expected, built into the math, a feature of the system rather than a signal that something has changed. Here is the simplest way I can illustrate this. If you flip a coin 1,000 times, you will see runs of 10, 12, sometimes 15 heads in a row. Not because the coin is biased, not because some force is pushing it toward heads, but because that is what randomness actually looks like when you generate enough data. People see the cluster and assume a cause. The math says you should expect clusters even without one. The cluster is real. The cause is imaginary. And telling the difference between those two things requires more than intuition. It requires data. So when someone looks at a single day with a super typhoon striking US territory, an earthquake on the same island chain, an asteroid inside the moon's orbit, record heat across the mid-Atlantic, tornado risk across the Midwest, and 13 red flag warnings on the plains, and says something is wrong, part of that reaction is the clustering illusion at work. Some of these events are genuinely, physically, mechanistically unrelated. The asteroid has nothing to do with the climate system. Its trajectory was set by orbital mechanics billions of years old. The earthquake was a tectonic event driven by plate subduction that operates on timescales of millions of years. Layering them together with atmospheric events into a single narrative of escalation is at least partially a cognitive artifact. Our brains doing what they evolved to do, finding patterns even where the connections are coincidental rather than causal. And this is the part where a lot of people check out. They hear clustering illusion and they interpret it as everything is fine, you are just imagining things, go back to sleep. That interpretation is wrong, and it is dangerously wrong, and I want to be very clear about why. The clustering illusion does not mean the trends are not real. It means you have to separate the perception of clustering from the statistical evidence for trends, and evaluate each one independently on its own merits, with its own data. You have to untangle the signal from the noise. And when you do that, when you set aside the asteroid and the earthquake and the psychological stacking effect, and focus specifically on the extreme weather events, the data tells a story that is impossible to dismiss. The number of Category 4 and 5 tropical cyclones globally has increased over the satellite era. Not by a trivial amount. James Cosson's 2020 paper in the Proceedings of the National Academy of Sciences, titled Global Increase in Major Tropical Cyclone Exceedance Probability Over the Past 4 Decades, documented that the proportion of storms reaching the highest intensity categories has shifted upward across multiple ocean basins between 1979 and 2017, at a rate that is unlikely to be explained by natural variability alone. The proportion of storms undergoing rapid intensification, that explosive, forecast-busting strengthening that Sinlaku exhibited, has gone up as the Bhatia paper we already cited found. Sea surface temperatures have risen in virtually every ocean basin on Earth as documented in the Cheng et al. Advances in Atmospheric Sciences series that publishes updated global ocean heat content estimates every year. The frequency of extreme precipitation events has increased in many regions, consistent with the basic physics of a warmer atmosphere holding more moisture. This is the Clausius-Clapeyron relation, and it is not a hypothesis. It is a thermodynamic identity, roughly 7% more atmospheric water vapor capacity per degree Celsius of warming. The number of billion-dollar weather disasters in the United States has roughly tripled per decade over the past 40 years, according to the National Oceanic and Atmospheric Administration's National Centers for Environmental Information. And that trend holds even after you adjust for inflation, population growth, and increased property values in vulnerable areas. These are not vibes, these are not perceptions. These are not feelings amplified by social media doom scrolling. These are measurements taken by instruments, recorded in datasets, analysed by researchers, published in peer-reviewed journals, replicated across independent groups using different methods. The signal is real, so the truth is layered, and it requires you to hold two things in your mind at the same time, which is uncomfortable but necessary. Yes, some of the feeling that everything is happening at once reflects normal cognitive bias, amplified by the way we consume information in 2026. Social media compresses every disaster into the same feed. 24-hour news cycles ensure that every extreme event gets maximum visibility. Your phone buzzes with alerts from 3 different states in the same afternoon. The information environment is designed, whether intentionally or not, to make clustering feel more intense than it is. A generation ago, the earthquake near Pagan and the red flag warnings in Kansas would not have appeared on the same screen at the same time. Now they do, and your brain processes them as a single escalating narrative because that is what brains do. But underneath that cognitive bias, underneath the social media amplification and the alert fatigue and the natural human tendency to connect dots that do not actually touch, there is a real, measurable, physically grounded signal. The climate system is producing more extreme events in more places during more months of the year, and the intervals between those events are compressing. The warm seasons are longer, the heat records are falling faster, the storms are intensifying more rapidly, the rainfall rates are increasing. The overlaps, the days when multiple regions face multiple hazards simultaneously, are becoming more common. Not because of some grand conspiracy or coordinated collapse, but because a system with more energy in it produces more energetic outcomes. That is not theory, that is thermodynamics. The clusters are partly illusory and partly real. The earthquake-typhoon coincidence is noise. The April super typhoon in a neutral ENSO year over abnormally warm ocean water is sick. The asteroid is irrelevant. The 303 simultaneous warnings across a country experiencing heat, fire, flood and tornado risk at the same time, that is a stress test result from a system being pushed harder than it was designed for. Separating those categories matters. Because if you lump everything together, you either panic about things that do not warrant it, or you dismiss everything because some of it was coincidence. And both of those responses lead to the same place: inaction. The challenge for all of us, scientists, journalists, policymakers, emergency managers, and yeah, you watching this right now, is to hold both of those truths simultaneously. To acknowledge the cognitive bias without using it as a reason to dismiss the trend. To see the pattern without inventing connections that are not there. To feel the weight of a day like today without surrendering to fatalism. And to respond to the evidence as it actually exists, not as we wish it were. Not as the conspiracy theorists frame it, not as the algorithm serves it, but as the instruments record it and the physics explain it. Because the evidence on a day like today is hard to ignore. And the question is not whether we are paying attention. The question is whether we are paying attention to the right things. Part 17. The new normal is not one event. If you have been watching the cosmic forecast for a while, you have heard me cover individual extreme events. Record-breaking storms, unprecedented heat, out-of-season cyclone, solar activity spiking in ways that raise eyebrows. Each time it is tempting to treat the event as a standalone story, a thing that happened, a thing we analyze, a thing we move on from until the next headline grabs our attention. That is how the news cycle works. That is how our brains work. Something dramatic happens, we focus on it intensely for a few days, and then the window closes and we file it away as that one time and move on with our lives. But Sinlaku is forcing a different kind of conversation. And I think if you have stayed with me this far, you can feel it too. Because Sinlaku is not a standalone story, it refuses to be contained in a single narrative. Every thread we have pulled in this video is connected to another thread, and that thread is connected to another. And at no point has the picture gotten simpler. It has only gotten more interconnected, more layered, more systemic. That is because what we are looking at is not an event, it is a data point in a pattern. And the pattern is not about any individual storm, any individual heat wave, any individual disaster. It is about the behavior of the system as a whole. The system being Earth's climate, the entire interconnected web of oceans, atmosphere, ice, land surfaces and energy flows that determines what weather is possible, where and when. That system is producing more energy. And I want to be very precise about this because precision matters when the stakes are this high. This is not a controversial statement. It is not a political position. It is not a prediction or a projection or a model output. It is a measurement. Instruments in the ocean have recorded increasing thermal energy content across virtually every basin. Atmospheric monitoring stations have recorded rising baseline temperatures on every continent. Satellite-derived datasets show more moisture in the atmosphere, consistent with the Clausius-Clapeyron relationship, the basic physics principle that warmer air holds more water vapor at a rate of roughly 7% more per degree of warming. These are numbers, they are recorded, they are verified. They are not going away because someone on social media does not like them. Now here is why that matters for understanding a day like today. That additional energy in the system does not manifest as one single, obvious catastrophe that you can point to and say, there it is, that is climate change. That is not how it works. And that misconception is one of the biggest obstacles to public understanding. What additional energy does is shift the statistical distribution of events. Imagine a bell curve, the familiar shape that describes the probability of different outcomes. Most days, most weather, most events cluster around the average. Extremes are rare, out on the tails of the distribution. That is normal. That is how the system has always worked. When you add energy to the system, the entire bell curve shifts. The average moves up. What used to be an unusually warm day becomes a normal day. What used to be a normal day becomes unusually cool. And out on the tails where the extremes live, the shift has disproportionate effect. Events that used to be extraordinarily rare, 1 in 100-year storms, 1 in 1,000-year heatwaves, become significantly more probable. Not because the system is doing something fundamentally new. It is doing the same thing it has always done, but it is doing it from a higher starting point. And that higher starting point means the extremes reach further, hit harder, and show up more often. And here is the piece that connects everything we have discussed today. When extremes become more frequent across multiple hazard types simultaneously, the probability of overlap increases. Not linearly, exponentially. If heat events are more common, and severe weather events are more common, and fire weather events are more common, and intense tropical cyclones are more common, the probability that 2 or 3 or 4 of those will occur on the same day goes up dramatically. It is the same math that governs why, if you roll 1 die, getting a 6 is unremarkable. But if you roll 5 dice and they all come up 6, something unusual has happened. Except in this case the dice are loaded, not by much, but enough that the full table 6s start showing up more often than the old odds would predict. This is the shift from single event thinking to systems thinking, and it is a shift that I think is essential for understanding where we are right now. Not just with Sinlaku, but with the trajectory we are on. Instead of asking why did this storm happen, a question with a specific satisfying contained answer, we ask why are conditions favourable for storms like this occurring more often, earlier in the year, with less recovery time between them. That is a harder question, it is less dramatic, it does not fit neatly into a headline. But it is the right question. Instead of asking why did the heat records break in April, we ask why is the baseline temperature from which April heat events launch now high enough to produce record-breaking departures during what should be a transitional season. Instead of asking why did 300 warnings go active on the same day, we ask why is the system producing enough simultaneous extremes that 300 warnings are becoming plausible on a single day. The answers to those questions all point in the same direction: more energy, higher baselines, shifted distributions, expanded seasons, compressed intervals. Sinlaku at 173 miles per hour in April. An earthquake the same day, unrelated but landing on the same community at the same time. 303 active weather warnings nationwide. Record heat in the mid-Atlantic that would have been remarkable in July, let alone April. Fire weather across the plains with 13 red flag warnings active simultaneously. Tornado risk across the Midwest driven by the same anomalous warmth feeding moisture into the collision zone with the jet stream. Flooding in the Great Lakes from persistent rainfall on saturated ground. An asteroid inside the moon's orbit, unrelated to everything else but adding to the psychological weight of a day that already felt like too much. None of these events caused each other. I have said that multiple times in this video, and I will say it again because it matters. The earthquake did not cause the typhoon, the heat did not cause the asteroid. These are independent occurrences. But the atmospheric events among them, the typhoon, the heat, the severe weather, the fire weather, the flooding, all share a common driver. They are all expressions of a climate system operating at a higher energy state than the one our infrastructure, our models, and our intuitions were built around. They occurred in the same 24-hour window not because of conspiracy or divine punishment or some unified forcing mechanism, but because a more energized system produces more extremes, and more extremes distributed in time produce more overlaps. It is statistics, it is physics, it is happening, the recovery windows are shrinking. We walk through this in detail with the CNMI, Utu-Mawar, Sinlaku. 3 catastrophic cyclones in 8 years on islands that need a decade to fully rebuild from each one. That is a localized version of a global trend. Communities worldwide are finding that the interval between disasters is shorter than the time needed to recover from the last one. Coastal cities, agricultural regions, island nations, river valleys, the geographic specifics vary. The underlying dynamic is the same. The result is not a new equilibrium. Not a new normal that communities adapt to and stabilize around. It is a downward ratchet. Each cycle starts from a lower baseline. Each recovery reaches a lower ceiling. The trend has a direction, and that direction is down. And the unpredictability is increasing in tandem. April super typhoons that no seasonal forecast anticipated. Rapid intensification events that outpace operational models, collapsing the window between warning and impact. Heat records broken not by tenths of a degree, the kind of incremental records that statisticians expect, but by margins of 5, 10, 15 degrees above normal that rewrite the statistical landscape entirely. The old patterns that guided planning for generations, the seasonal calendars that told you when to prepare and when to relax, the ENSO-based predictions that gave you a framework for what kind of year to expect, the building codes designed around historical maximums that were supposed to represent the worst-case scenario, are increasingly inadequate guides to the present. They are not wrong about the relative relationships. They are calibrated to a world that is receding in the rearview mirror. This is not one event. I know the title of this video is about one storm, I know the thumbnail shows one cyclone. I know the hook that brought you here was about Sinlaku, about the CNMI, about the strongest storm on Earth making landfall on American soil in a month when it should not exist. And all of that is true and all of it matters, but the story is bigger than Sinlaku. The story is a trajectory, a curve on a graph that has been bending in the same direction for decades. And that is now steep enough that individual data points, individual storms, individual heat waves, individual days with 300 warnings are reaching values that the old frameworks never imagined. And trajectories, unlike events, do not end. Events have a beginning and a conclusion. The storm arrives and the storm passes, the heat wave builds and the heat wave breaks. The waters rise and the waters recede. You can mark them on a calendar and move on. Trajectories do not work like that. They continue, they persist, they compound. They keep going in the same direction until something, a force, a decision, a fundamental change in the system, alters their course. Nothing has altered this course yet. And until something does, every year will produce new data points, new records, new days when the map lights up from coast to coast, and new communities discovering that the world they prepared for is no longer the world they live in. Part 18. Infrastructure versus reality. Every piece of infrastructure on Tinian and Saipan was designed for a world that no longer exists. I want you to sit with that sentence for a moment, because it sounds like hyperbole. It sounds like the kind of dramatic overstatement that a narrator throws in for effect. It is not. It is an engineering reality grounded in how buildings, roads, power systems, and coastal defences are actually designed, funded, and constructed. And understanding it is essential to understanding why what is happening on these islands right now is not just a natural disaster. It is a systems failure. Not of the people who built the infrastructure, but of the assumptions they were given to build it around. Here is how infrastructure design works in practice. Building codes are based on historical weather data. Engineers and code developers look at the worst conditions observed over a given period, typically 50 to 100 years of records, and they extract the extreme values. The highest wind speed recorded, the maximum storm surge observed, the most intense rainfall rate measured. They take those historical extremes, add a safety margin, typically somewhere between 10 and 30%, depending on the hazard and the structure type, and that becomes the design standard. The number that the building has to withstand, the load the roof has to resist. The height the seawall has to reach, the flow rate the drainage system has to handle. A building code in the Mariana Islands accounts for typhoon force winds because typhoons are a known hazard in the Western Pacific. It specifies wind load requirements calculated from historical typhoon data. It mandates roof tie-down specifications designed to resist uplift forces consistent with observed storm. It sets concrete reinforcement schedules intended to prevent structural failure under the kind of lateral loads that historical typhoons have produced. It establishes elevation minimums for construction in storm surge zones based on the highest surge levels documented in the historical record. Every number in that code traces back to a dataset, and every dataset has a time boundary. It captures what the climate did during the period of observation. The problem, and it is a problem that extends far beyond the CNMI, far beyond typhoons, far beyond any single hazard type, is that historically is no longer a reliable guide to currently, and the gap between the two is widening with every passing year. When the strongest tropical cyclone ever to strike United States soil hits your island in 2018, U2, 180 miles per hour, the historical record gets revised. That data point becomes the new extreme. In theory, the next round of code updates should incorporate it. The design standard should ratchet up. Future construction should account for the new reality that Category 5 landfalls on these islands are not theoretical but documented. When another major storm hits 5 years later, Mawar in 2023, the record gets revised again. The dataset now includes 2 major events in rapid succession, which changes not just the peak values but the frequency assumption. A code designed around the premise that a Category 5 landfall is a once in 50 years event now has to reckon with data suggesting the return interval might be much shorter. When a third catastrophic cyclone strikes 3 years after that, Sinlaku in 2026, with winds of 173 miles per hour and a forward speed of 3 knots, meaning the storm sits over the islands for the better part of a full day, the historical record is not just being revised. It is being rewritten in real time. The assumptions that underpinned every building, every seawall, every power line, and every drainage culvert on those islands are being invalidated, while the structures built on those assumptions are simultaneously being destroyed by the conditions that invalidated them. The infrastructure is not failing because it was poorly built. It is failing because it was built correctly for a climate that no longer matches the one delivering the loads. The buildings met code, the code was based on data, the data is obsolete. And the lag between when the climate shifted and when the codes, the funding, and the construction practices catch up is the window in which communities get hurt. And I need to emphasize this, the CNMI is not a special case, it is an extreme case. But the underlying dynamic is playing out everywhere, across every type of infrastructure, in every region that faces weather-related hazards, which is essentially everywhere. Power grids across the United States were designed for historical temperature ranges. The transformers that step voltage down for residential delivery are rated for specific ambient temperature conditions. When summer heat exceeds those conditions, and it is exceeding them more frequently in more places every year, the transformers overheat. Their cooling systems cannot keep up, efficiency drops, failure rates increase. At the same time, demand spikes because everyone turns on their air conditioning simultaneously, pushing load above the generation and transmission capacity that was planned around historical peak demand curves. The result is cascading blackouts, not because the grid is broken, because the grid was designed for a temperature regime that has shifted out from under it. Coastal flood defences tell the same story from a different angle. Seawalls, levees, tidal barriers and beach nourishment projects were engineered for historical surge heights and sea levels. Those heights were extracted from decades of tide gauge records and storm surge observations. The designs included safety margins, they were good engineering. But when storms produce surge that exceeds the historical envelope, because the storms are more intense, or slower moving, or arriving on top of a baseline sea level that has risen several inches since the structure was designed, the defences are overtopped. Water goes where it was never supposed to go, and the communities behind the wall who were told they were protected discover that the protection was calibrated to a pass that is no longer predictive. Drainage systems might be the most universal example. Every city, every town, every developed area on Earth has some form of stormwater management. Storm drains, culverts, retention ponds, drainage channels. Those systems are sized for specific rainfall intensities. A drainage engineer calculates the expected flow from a storm of a given severity, say a 1 in 25-year rainfall event, and designs pipes and channels large enough to handle that flow. The problem is that a 1 in 25-year event under the old climate baseline might now be a 1 in 10-year event under current conditions. And a 1 in 100-year event, the kind that is supposed to be the absolute worst-case scenario that only the most critical infrastructure needs to handle, might now occur every 30 or 40 years. The pipes have not shrunk, the rain has increased. And when Sinlaku sits over Tinian and Saipan dumping 1 to 2 inches per hour for 10 straight hours, a total rainfall that exceeds the design capacity of every drainage system on those islands by a factor of 2 or 3, the system does not malfunction. It does exactly what the math says it will do when the inputs exceed the parameters. It overflows. Water runs across the surface, through buildings, down slopes into communities, carrying debris and mud, and everything else that is not anchored down. It is not a malfunction, it is a math problem, and the math has changed. The CNMI's infrastructure challenges are an extreme case of this universal mismatch, but they illustrate the core problem with painful clarity. The gap between what we have built and what we now need is growing. Every year the climate continues to shift. The infrastructure designed for the old regime falls further behind. Closing that gap requires not just rebuilding damaged structures, which is what happens after every disaster, but rebuilding them to standards that account for the new reality. Higher wind ratings, greater surge resilience, more drainage capacity, longer duration loads. And perhaps most importantly, shorter return intervals between design events, which means the infrastructure has to be more durable, more maintainable, and more resilient to repeated stress rather than single event peak loads. All of that is more expensive, significantly more expensive. A building designed to withstand 180 mile/hour winds costs more than one designed for 140. A seawall built for 15 feet of surge costs more than one built for 10. A drainage system sized for extreme tropical cyclone rainfall rates costs more than one sized for typical thunderstorm runoff. And these costs multiply across every structure, every system, every piece of infrastructure on every island. The price tag for rebuilding the CNMI to genuinely storm resilient standards, not just patching what broke, but building something that can withstand the next Sinlaku, is staggering for a territory with a small economy and limited fiscal capacity. It also takes longer. You cannot just throw money at reconstruction and expect it to happen overnight, especially on remote islands with constrained supply chains and limited construction labour. A comprehensive infrastructure rebuild of the CNMI, done to modern standards, would take years, even under ideal conditions. And the conditions are not ideal, they never are after a disaster. And it requires political commitment to fund infrastructure for a future that, by definition, has not arrived yet, based on projections that some stakeholders still dispute, and in competition with every other demand on the federal budget. That is the political reality. Asking Congress to appropriate billions of dollars to harden a territory that most Americans cannot find on a map against storms that the current building codes technically do not require you to plan for, based on climate projections that a segment of the political spectrum challenges. That is a heavy lift. and it is a lift that has to be repeated after every storm, in a cycle that never ends. And even if the money were unlimited and the political will were absolute, even in that fantasy scenario, there is a temporal problem that no amount of funding can solve. You cannot rebuild an entire island's infrastructure between storms when the storms are arriving every 3 to 5 years. The construction timeline exceeds the return interval, full stop. You cannot pour and cure concrete, fabricate and install steel reinforcement, lay underground utilities, rebuild the power grid, reconstruct the housing stock and harden public facilities in 3 years. Not on a remote island, not even on a mainland with full logistics access. The clock runs out before the work is done, so what happens instead is triage. You identify the most critical structures, the hospital, the emergency operations centre, the primary shelter facilities, and you harden those first. You reinforce the communications infrastructure so you do not lose contact with the outside world. You patch the power grid enough to restore basic service. And everything else, the schools, the homes, the commercial buildings, the roads, the secondary systems, takes its chances. You hope the next storm is weaker, you hope it tracks further away, you hope you get lucky. And when you do not get lucky, when the next storm arrives at full strength, and the infrastructure is not ready because it could not possibly be ready in the time available, the damage compounds again, the baseline drops again, and the cycle continues. That is the position the Commonwealth of the Northern Mariana Islands is in right now, tonight, as the strongest storm on Earth grinds overhead at walking speed. The buildings absorbing those winds are not the buildings they should be. They are the buildings that time, money, logistics, and the cruel mathematics of storm recurrence allowed them to be. And the gap between what they are and what they would need to be to survive this night intact is a gap that was always going to be filled by damage, by loss, and by the slow, exhausting realization that the world these islands were built for is not the world they exist in anymore. Part 19, the information war layer. Within hours of Sinlaku's intensification, before the eyewall had even made contact with Tinian, social media platforms began circulating a predictable set of alternative narratives. And I say predictable not to be dismissive, but because this has become as reliable a feature of extreme weather events as the storm surge itself. The pattern repeats every single time a major storm forms. It intensifies rapidly. It threatens populated areas. And before the first wind gust hits the first building, the conspiracy ecosystem activates. Some users claim the storm was evidence of geoengineering, weather manipulation technology deployed by unnamed government actors for unstated purposes. The specific claims varied. Some pointed to HAARP, the High-Frequency Active Auroral Research Program in Alaska, which has been a favourite target of weather conspiracy theorists for decades, despite being an ionospheric research facility with no capability to influence tropical cyclones. Others referenced vague cloud seeding operations, conflating real but extremely limited cloud seeding technology, which can modestly enhance precipitation in specific local conditions, with the ability to create or steer a Category 5 super typhoon across thousands of miles of open ocean. The leap between those two capabilities is roughly equivalent to the leap between lighting a match and detonating a nuclear weapon. But the distinction gets lost in the scroll. Others pointed to the proximity of US. Military installations on Guam, Anderson Air Force Base, Naval Base Guam, the broader strategic military presence in the Marianas, and speculated that the storm was somehow connected to classified weapons testing. The logic, such as it was, ran something like, the military is there, the storm is there, therefore the military caused the storm. Some accounts went further, suggesting directed energy weapons or atmospheric manipulation technology being tested under cover of a natural disaster. A subset of these accounts linked the earthquake to the typhoon, claiming that the magnitude 5 seismic events 6 hours before landfall was evidence of tectonic weapons, or underground detonations designed to destabilize the region in coordination with the atmospheric assault. I want to be straightforward with you about all of this, because I think you deserve straightforward treatment. None of these claims have evidentiary support, not partial support, not ambiguous support, none. The technology required to create a tropical cyclone from scratch, to organize convection across hundreds of miles of ocean, to spin up a vortex with sustained winds exceeding 170 miles per hour, to maintain that system for days as it tracks across the Pacific, does not exist. It is not classified, it is not hidden, it does not exist. The energy budget of a mature super typhoon is so astronomically large that no human technology comes within orders of magnitude of replicating it. To put a number on it, a mature Category 5 tropical cyclone releases thermal energy at rates on the order of 5 times 10 to the 14th watts. For comparison, total global electricity generation is on the order of 3 times 10 to the 12th watts. The storm outputs roughly 100 to 200 times the entire electrical output of human civilization, continuously, for days. We cannot create these storms, we cannot steer them. We can barely predict them accurately more than a few days in advance. The idea that any government possesses the capability to engineer what Sinlaku did is not a fringe theory that deserves respectful consideration. It is a fundamental misunderstanding of the scale of energy involved. The physics of tropical cyclone formation and intensification are well understood. We have walked through them in detail in this video. The ocean heat content, the low wind shear, the atmospheric moisture, the steering current collapse, the rapid intensification dynamics. Every aspect of Sinlaku's behaviour is consistent with the observed environmental condition. There is no residual mystery requiring an exotic explanation. The ocean was anomalously warm. The atmosphere was anomalously favourable. The storm responded exactly as physics predicts a tropical cyclone would respond under those conditions. The explanation is complete. It is just not exciting enough for a conspiracy thread. The earthquake was a deep-focused seismic event at 219 kilometers depth, occurring in one of the most seismically active subduction zones on the planet. The Mariana Trench system produces thousands of earthquakes per year, a magnitude 5. 5 at that depth is notable but not unusual. No physical mechanism exists by which a tectonic event at that depth could influence atmospheric conditions or vice versa. The timing was coincidental. Coincidences happen. They happen more often than our pattern-seeking brains want to admit. And the inability to accept coincidence is one of the primary psychological engines driving conspiracy thinking. Now, here is where I need to shift from debunking to something more important. Because the existence of these narratives matters, not because they are true, but because of what they do to the information environment during exactly the moments when accurate information is most critical. And this is the part of the story that does not get enough attention, because it is less dramatic than the storm itself, but potentially just as damaging. When a community is facing a super typhoon, when families are deciding whether to evacuate or shelter in place, when emergency managers are issuing life or death directives, when first responders are pre-positioning resources based on forecast tracks and intensity projections, the last thing anyone needs is a significant fraction of the population doubting whether the storm is real, whether the official warnings are trustworthy, or whether the government issuing those warnings is secretly the entity that created the threat. Conspiracy narratives do not just distract. They actively corrode the trust that emergency communication depends on. If someone believes the government is engineering hurricanes, why would they trust the government's evacuation order? If someone thinks the National Weather Service is part of the cover-up, why would they believe the wind speed forecast? If someone is convinced that the earthquake was a weapons test, why would they follow the guidance of the same military that they believe caused the destruction? Every layer of conspiracy thinking removes a layer of trust. And trust is the only thing that makes emergency communication work. You can have the most accurate forecast in the world, issued by the most competent meteorologists on the planet, and it means nothing if the people who need to act on it do not believe it is real. Confusion does not just slow response. In the context of a Category 5 landfall, confusion can kill people. A family that delays sheltering because they are not sure the storm is legitimate. A community leader who questions whether to open the emergency shelter because half the comments on their social media post are claiming the storm is fake. A resident who stays in a surge zone because they have been told online that the government is exaggerating the threat to justify some hidden agenda. These are not hypothetical scenarios. They are documented consequences of conspiracy-driven distrust during natural disasters. And they become more common with every passing year as the information ecosystem becomes more fractured and more algorithmically optimized for engagement over accuracy. And here is the part that keeps me up at night as someone who does this work. The real story, the true explanation for what is happening, is less dramatic than the conspiracy and harder to condense into a social media post. The truth is that the climate system is producing more energy, which is shifting the statistical distribution of extreme events, which is increasing the frequency and intensity of overlapping hazards, which is compressing recovery windows, which is degrading infrastructure faster than it can be rebuilt. That is the real story, and it is a story that requires nuance. It requires understanding ocean heat dynamics and atmospheric physics and statistical distributions and infrastructure engineering and economic constraints and policy timeline. It does not have a villain. It does not have a smoking gun. It does not have a secret laboratory or a shadowy government program. It has trends, probabilities, compound risks, feedback loops, and a timeline that stretches across decades. Compare that to the government has a weather weapon, 6 words, instantly engaging, emotionally charged, shares beautifully, generates enormous engagement because people either passionately agree or passionately argue against it, and the algorithm does not care which. It rewards the interaction regardless. The conspiracy post gets 1 million views in an hour. The careful scientific explanation gets buried on page 3. This is where evidence-based communication faces its hardest test. Not in the laboratory. Not in the peer-reviewed journal. Not at the scientific conference where everyone already agrees on the methodology. The hardest test is in the information environment during an active disaster, where speed beats accuracy and narratives beat data. We're the work of channels like this one, of forecasters who spent years in school learning fluid dynamics and thermodynamics, of researchers who have devoted careers to building the knowledge base that explains events like Sinlaku. All of that work has to compete in real time with content that was designed not to inform but to exploit confusion. Content that does not need to be right, it just needs to be first and loud and emotionally resonant. The challenge is not just debunking false claims. If it were, this would be easier. You would just post the facts, cite the sources, and move on. The challenge is making the true story compelling enough that it does not lose the audience to simpler, more emotionally satisfying narratives. Because the true story, that overlapping extremes are increasing, that recovery windows are shrinking, that infrastructure is falling behind the curve, that communities are caught in a ratcheting cycle they cannot outrun, that story demands action. And action requires understanding, and understanding requires attention. And attention is exactly what gets fractured, splintered, and scattered when the information space fills with noise that is engineered to be more engaging than the truth. I do not have a clean solution to this, nobody does. But I think part of the answer is what we have been doing for the last hour of this video. Walking through the real physics, the real data, the real mechanisms in enough detail that you can see the full picture for yourself and evaluate it on its merits. Not because I told you to believe it, because you followed the logic and it held up. That is the only durable antidote to misinformation. Not just correcting the false claim, but building the real understanding deeply enough that the false claim cannot find a foothold. The storm is real, the earthquake was real, the pattern of escalating, overlapping hazards is real. The explanation is physics, not conspiracy. And here is the part that should actually concern you. The implications of the real explanation are far more serious than anything a geoengineering theory could suggest. Because if the government had a weather weapon, at least theoretically, they could turn it off. Physics does not turn off. The ocean heat does not dissipate because the news cycle moves on. The shifted baseline does not reset because a politician gives a speech. The trajectory we have been tracking through this entire video, more extremes, more overlaps, more damage, less recovery time, that trajectory continues whether anyone is paying attention to it or not. And it will still be continuing long after the conspiracy posts have been forgotten and the algorithm has moved on to the next outrage. That is why the information war matters, not because the conspiracies are dangerous in themselves. Most of them are too incoherent to drive organised action, but because they consume the attention and erode the trust that we need to respond to the real problem. And the real problem is not going away. Part 20, final frame. This is a preview. Let me take you back to where we started. Right now, as this script reaches you, Super Typhoon Sinlaku is crossing the Mariana Islands. 173 miles per hour at peak intensity, 3-knot forward speed. Eyewall residence time measured in the better part of a day. 15 to 25 inches of rain falling on islands with steep terrain and limited drainage. 10 to 15 feet of storm surge on coastlines with overtopped reefs and compromised seawalls. 40-foot seas, extreme wind warnings active. Infrastructure pre-weakened by 9+ hours of hurricane-force winds before the eyewall even arrived. This is happening on United States soil in April. 6 hours before the eyewall made contact, a magnitude 5. 5 earthquakes shook the same island chain, unrelated to the storm, but real and felt by the same people now sheltering from the most violent winds they have experienced since U2 in 2018. A storm that many of them, and many of their homes and schools and hospitals, never fully recovered from. While all of this unfolds in the Pacific, the continental United States is running 303 simultaneous weather warnings. The Mid-Atlantic is breaking April heat records by margins of 15 to 30 degrees. Iowa and the Great Lakes are under enhanced severe weather risk with tornado potential. 13 red flag warnings are active across the high plains. Michigan and Wisconsin are flooding. And an asteroid is passing inside the moon's orbit. None of these events caused each other. I have said that multiple times in this video, and I will say it again because it matters. The earthquake did not cause the typhoon. The heat wave did not cause the tornadoes. The asteroid has nothing to do with any of it. But they all occurred in the same 24-hour window, on the same planet, affecting the same country, stressing the same response systems. And in the case of the weather events, among them, emerging from the same fundamental driver. A climate system carrying more energy than the one we built our civilization around. Sinlaku is not an anomaly, is a data point. One more entry in a growing catalogue of events that exceed historical expectations, arrive outside traditional seasonal windows, compound on communities still recovering from the last disaster, and occur alongside other extremes that collectively overwhelm the capacity of response systems designed for a less volatile world. The recovery gap is widening. U2 to Mawar was 5 years, Mawar to Sinlaku was 3. The infrastructure was not ready. The budget was not there. The buildings were not whole. And the next storm, whenever it comes, will find islands that are once again partially rebuilt, partially functional, partially prepared. The ratchet clicks down. The season is expanding. April super typhoons were supposed to be once-in-a-generation anomalies. If the ocean keeps warming, if the warm pool keeps deepening, if the conditions favourable for explosive intensification keep occurring earlier in the calendar year, then the season, as we have understood it for a century, is becoming obsolete. The walls of the box are moving outward, and everything inside the box, our forecasts, our building codes, our insurance models, our sense of when to be ready, has to move with it or get left behind. The overlaps are intensifying. Not because some malevolent force is coordinating disasters, but because a more energized system produces more events, and more events distributed in time inevitably cluster more often. The days when everything goes wrong simultaneously are not being engineered. They are being statistically generated by a climate system that has more dice in play and is rolling them more often. And the information environment is fracturing at exactly the moment it needs to cohere. While researchers work to understand and communicate these compounding risks, the public discourse splits between denial, conspiracy, fatalism, and the increasingly desperate work of people trying to communicate the truth with enough clarity and urgency to drive meaningful response. Sinlaku will eventually pass, the winds will drop, the surge will recede, the rain will stop. The CNMI will begin the agonizing, familiar process of assessing damage, clearing debris, restoring power, and rebuilding again. The headlines will move on, the asteroid will disappear into its long orbit. The heat wave will break, the fires will be contained, the floodwaters will drain, and the system will keep warming, the ocean will keep accumulating heat, the dice will keep rolling. And the next day like this one, the next day when everything stacks, when every warning lights up, when a community that never fully recovered takes another hit from a storm that should not exist in the month it arrived, that day will come again. Sooner than the last interval, on infrastructure weaker than the last rebuild. With recovery resources stretched thinner than the last time. This is not a story about one storm. This is a story about a system in transition, and the communities caught inside that transition, and the institutions struggling to keep pace with it, and the gap growing wider with every passing year between the world we prepared for and the world we now live in. The question is not why this happened. The question is how often it happens next. If you made it to the end of this, thank you for staying with me. The reason I built the Cosmic Forecast was to give people a place where the science of what is happening to our climate, our oceans, our storms, and our sky is presented at full complexity, without dumbing it down and without hyping it up. Sinlaku is not the last storm we will cover. It is not the last April super typhoon we will cover. It is not the last day when the map lights up from coast to coast. If you want to be here for the next one, and the one after that, and the one after that, subscribe to the Cosmic Forecast. Turn on notifications, because rapid intensification is not just a property of storms anymore. It is a property of the pace at which the story itself is unfolding. Drop me a comment. Tell me where you are watching from, what time it is where you are, and whether the pattern I have laid out over the last 20 parts matches what you are seeing in your own region. Because the only way any of us make sense of a trajectory this big is by comparing notes. Take care of yourself. Take care of the people around you, and I will see you in the next one. The Cosmic Forecast.